Hello, friends, and welcome back to the Snoozy Scientist, where we gently wander through the mysteries of science, one sleepy yawn at a time. Whether you're listening from the comfort of your bed, wrapped in a blanket, or floating in that dreamy space between waking and sleeping, you're exactly where you need to be. Tonight, we are traveling into a world sealed beneath ice, older than memory itself, a silent realm shaped by cold and time. Down here, beneath a frozen ceiling that has not seen sunlight for millions of years, the planet reveals one of its strangest and most isolated ecosystems. Water flows through hidden valleys where shadows have reigned since long before humans existed. In these dark places, life persists in forms that stretch our understanding of biology. Microbes feed on minerals rising from stone. When scientists first lowered cameras beneath its ice shelf, they expected an empty void, but instead, they recorded moving shadows drifting across the lens. Tiny creatures drift through black seawater, guided by chemical whispers rather than sight. And beneath the thickest ice, ancient lakes hold waters untouched by the sun for more than 15 million years. In this quiet darkness, evolution follows rules unlike anywhere else on Earth. The cold slows the rhythm of living things until a single lifetime can span decades. Pressure squeezes the familiar into the unfamiliar. Molecules appear that do not match surface life. And everywhere, the boundary between ancient and modern worlds feels strangely thin. But why has life adapted so patiently in a place where almost nothing should survive? What secrets are held in waters untouched by the sun for millions of years? How do organisms endure where warmth cannot reach and sunlight never enters? And what does this hidden realm reveal about the possibilities of life far beyond our world? Tonight, we drift deeper into the silence beneath Antarctica, letting its frozen mysteries unfold, one gentle layer at a time. But before we begin, if you enjoy videos like this, slow, soothing, and quietly filled with wonder, I'd love it if you gave this one a like and maybe tap subscribe. It helps more curious minds like you find their way to this peaceful little corner of the internet and lets the algorithm know that sleep and science go perfectly together. And if you'd be so kind, let me know in the comments, where are you winding down from tonight and what time is it there? It's always a joy to see how far across the world this little sleepy corner of science travels. Now take a deep breath, let your shoulders soften, and together let us drift beneath the quiet weight of the Antarctic ice. Long before the creatures beneath the ice learned to glow, or drift, or survive in silence, the land that would cradle them was warm. Ancient forests once covered its valleys, and shallow seas washed gently across its coasts. That warmth is only a memory now, softened by time, yet it rests quietly behind everything Antarctica has become. To understand the hidden world beneath its frozen ceiling, we must step back into an age when the continent still breathed in sunlight and green life. The transformation that followed reshaped not only a landscape, but the very rules that life would follow. For millions of years, the southern continents drifted slowly across the planet, carried by the deep and patient movement of Earth's mantle. As they shifted, Antarctica was pushed farther south until it settled near the pole, like a sleeping giant. Even then, ice had not yet claimed it. The air moved differently, the oceans flowed along gentler paths, and warmth still had a way of finding the land. But slow movements rarely stay simple. The continents around Antarctica continued to shift, and the seaways that separated them began to widen. A quiet doorway opened between South America and Antarctica, and another formed between Australia and the South Polar waters. These narrow gateways would become the first hints of a world about to change. As the openings widened, The ocean found a new freedom. Currents that once touched many shores began to slip through the southern passages without interruption. Over time, they merged into a single wandering path that flowed around Antarctica in a broad circle. The water gathered speed, drawn by the pull of the planet's rotation and the vastness of its route. It became the Antarctic Circumpolar Current, a loop so powerful that it isolated the continent from the rest of the ocean. Warm water could no longer reach its coasts. The circle held firm, a tireless ribbon of cold laying claim to the far south. When the current grew strong enough, a shift in climate began. The air that once carried moisture and warmth across the southern hemisphere now found a barrier in the spinning waters. Storms changed their patterns and traveled along new routes. The skies above Antarctica gradually lost the softness of earlier ages. Winters deepened, summers shortened. Each year left a little more snow behind than it took away. Slowly, layer upon layer, ice formed. What began as a thin seasonal covering expanded until it became a permanent presence. Over thousands of years, those layers thickened into a vast ice sheet that pressed down with the weight of mountains. Sea levels across the world responded to the growing cold as ice built itself into towering shelves and broad domes across the continent. The ocean lowered and reshaped coastlines far beyond the polar circle. New land appeared in scattered regions, while other areas dried into deep basins. The balance of water between continents shifted, changing how winds moved across the planet. Atmospheric currents adjusted like threads in a loom, weaving new patterns that only deepened the chill surrounding Antarctica. The entire southern hemisphere began to feel the influence of this icy anchor. Once the deep freeze settled in fully, Antarctica became a world apart. The ice sheet grew thick enough to silence the land beneath it, hiding valleys, mountains, and ancient riverbeds. Beneath its weight, the crust of the earth bent and formed new basins that filled with water so isolated that sunlight would never touch them again. In this quiet, sealed realm, cold reigned without rival. The rhythms of life changed. Only creatures that could survive slow growth, scarce nutrients, and frigid darkness remained. Many vanished, yet some learned to adapt so gradually that the transformation feels like a whisper in the fossil record. The freezing of Antarctica did more than create a landscape. It separated the continent from the global conversation of oceans and atmosphere. The circumpolar current circled it like a guardian, preventing warm waters from returning and trapping cold waters beneath drifting ice shelves. This isolation turned Antarctica into a self-contained world, a biological universe with its own rules. Organisms within it experienced pressures that few other places could offer, from crushing cold to deep, oxygen-rich waters that encouraged unusual growth and astonishing resilience. As the ice thickened over the ages, the creatures beneath it found themselves living in near timeless conditions. Seasonal change softened into quiet cycles. Organic material drifted slowly through water that rarely mixed with the open ocean. Chemical gradients formed in places where brines sank like heavy rivers, and mineral-rich water rose along volcanic ridges hidden deep below. Life began to follow pathways that would never form in warmer environments. What survived did so by embracing the stillness. By the time Antarctica fully transformed into the frozen world we know today, its identity had become inseparable from its isolation. The continent, once warm and vibrant, now held a silent strength shaped by cold. This strength created habitats that defied expectations, from subglacial lakes cut off for millions of years, to deep ocean shelves where strange giants wandered slowly through darkness. Every creature that lives there now carries a memory of that long transformation, etched into bone, blood, or cell. The story of how Antarctica became a planet of ice is not one of sudden change, but of patient, relentless motion. It is a story written in drifting continents, shifting winds and currents that circle the world with quiet power. It is the foundation upon which every later discovery rests. Only by understanding how the cold took hold can we begin to see why the hidden world beneath the ice feels so ancient and so separate, as if it belongs to another age of Earth entirely. The Ross Ice Shelf stretches across the Southern Ocean like a vast frozen curtain, hiding an underside that sunlight has not touched for longer than human memory can measure. Its surface appears still from above, quiet and white, yet beneath it lies a realm shaped by slow moving currents and ancient darkness. Still, even with all that curiosity, they expected silence, they expected emptiness. Very few believed they would ever witness movement in a place that seemed so sealed away from time. When researchers finally lowered a small camera through a narrow borehole drilled deep into the shelf, the descent felt like sending a single thread into a world of black water. The opening itself was only wide enough for the instrument to pass, just a circle of darkness glowing against the pale ice around it. Meltwater dripped gently from its edge. As the camera slipped downward, the light from the surface faded until it became a faint memory. The water accepted the device without resistance, as if it had been waiting for this moment. At first, the footage showed only what everyone expected. Tiny grains of sediment drifted past the lens like falling dust. Faint ribbons of ice crystals shimmered near the walls of the borehole. The water was calm and cold, so cold that every sound from the surface seemed to vanish before reaching the lower depths. The camera moved slowly, guided by rope and careful hands far above. There was nothing unusual, nothing that hinted at the possibility of life in a place walled off by hundreds of meters of ice. When the camera finally broke through into open seawater beneath the shelf, the view widened into a darkness so deep it felt like a landscape of its own. A small light on the device reached only a limited distance, carving a narrow cone of visibility into the black. The water beyond the beam remained hidden. Scientists had seen this before in earlier missions and earlier attempts. Still water, silence, a world that seemed too cold and too distant from sunlight to stir. Then, gently and almost without shape, something moved. It was only the faintest shift at first, a soft interruption of the light reflected from drifting ice particles. A shadow glided across the edge of the frame, so subtle that the team watching the feed almost missed it. The camera kept sinking, its beam sweeping slowly along the empty space. A few moments later, another motion appeared. This time it was clearer. Something passed through the light, not touching the camera, not approaching with purpose, simply drifting with a graceful certainty. It was larger than any particle in the water. It had weight. It had presence. In that small room far above the ice shelf, the researchers leaned closer to the monitors. There was no alarm, only a quiet shift in attention, the kind that comes when the unexpected brushes against careful expectation. The scientists had prepared themselves for solitude. To see movement here, in a place colder and more isolated than nearly any environment on Earth, was astonishing. The camera continued downward until it reached the depth where it would stop. Its beam stood still, a pale column of light reaching across a small pocket of the under-ice sea. Within that beam, another shape moved. This time it lingered at the edge, appearing and disappearing like a thought that refused to fully form. It did not seem threatening or hurried. Instead, it carried the slow rhythm of an organism that had adapted to darkness, so complete that speed was unnecessary. For a long moment, nothing else shifted. The shadow faded into the distance, leaving tiny particles swirling in its wake. The water regained its calm, yet the presence of that single movement changed everything. It suggested that life in some form existed here. Not only microscopic life, which scientists had suspected for years, but something large enough to cast a visible silhouette in the beam of a descending camera. What made the discovery so remarkable was the sheer improbability of survival in this place. Beneath hundreds of meters of ice, the ocean receives no light from the surface. Temperature hovers near the freezing point of seawater, and nutrients arrive only through slow drifts of material carried from far away or through faint chemical traces leaked from rock and ice. Any creature living here must endure pressure, darkness, scarcity, and cold in ways that few organisms elsewhere on Earth ever experience. That first glimpse of movement, faint and almost dreamlike, opened new questions. Scientists began to wonder whether the under ice seas of Antarctica might hold more than microbial colonies. Perhaps subtle networks of creatures had learned to survive in the quiet world below, feeding on drifting particles or on each other in rhythms too slow for ordinary oceans. Maybe life had shaped itself into forms that made perfect sense only in this deep and ancient cold. The camera was eventually raised back through the borehole, carrying with it footage that would be studied for months. No one claimed to know exactly what had passed through the light. The shapes were too distant, too softly defined, yet the images were clear enough to show that something alive had been there. In a continent shaped by silence and ice, even a small motion becomes a story that lingers. The footage did not offer answers, it offered possibility. And in a world where sunlight never enters, and where time moves with a different pace, possibility is enough to shift the imagination of science. Far beneath the winds that sweep across Antarctica, in waters that remain cold and steady through every season, lives a group of creatures shaped by the quiet patience of the continent itself. Their world never warms, not even for a moment. Here, the ocean holds a temperature so close to freezing that most animals would slip into stillness long before they reached these depths. Yet some species move through this cold as if it were their natural breath, drifting slowly through pale water with a grace that mirrors the long calm of the ice above. Among them is a family of fish unlike any other on Earth. They are the icefish, pale and almost ghost-like, with bodies that appear carved from frost. In the soft light that filters through the under-ice world, their skin carries a faint shimmer, as if they are made of translucent stone. Their greatest secret lies deep inside them, flowing quietly through vessels that would look empty to us. They are the first known vertebrates that live without hemoglobin, the red pigment that carries oxygen in the blood of nearly every other animal. Most creatures depend on hemoglobin, the way forests depend on rain. Without it, cells starve, muscles falter, and life quickly fades. But the icefish thrive in waters where oxygen dissolves easily into the cold. The chill that would paralyze warm-blooded animals becomes their advantage. The water around them holds enough oxygen to seep directly into their blood plasma, allowing it to move slowly through their bodies without the need for the pigment that colors our own blood. Their circulation is gentle, almost unhurried, following the rhythm of their world. Because their blood contains no hemoglobin, it appears almost clear, tinged only slightly with the soft hues of the tissues around it. When scientists first examined these creatures, the absence of red was startling. It challenged expectations in a way that felt almost dreamlike. How could such fragile-looking fish survive in a place where the temperature would freeze most animals from the inside out? The answer lies in another quiet adaptation, one that grew over millions of years in response to the deep cold. The icefish possess special proteins, winding molecules that drift through their blood and tissues like tiny protectors. These are antifreeze proteins, capable of binding to microscopic ice crystals before they can grow. Without them, even the slight chill that touches seawater at these depths would be enough to form crystals inside the body, slowly tearing cells apart. With them, the fish move safely through waters that hover just above the freezing point. These proteins do not warm the fish. They simply prevent the formation of internal ice, allowing the animal to remain fluid and alive in an environment where other creatures would solidify long before reaching such depths. Their presence is a reminder that evolution often works quietly, solving problems one small step at a time, shaping life in ways that can seem almost delicate. The icefish body carries other traces of this long history. Their hearts are large for their size, beating with a slow power that pushes oxygen rich plasma through wide vessels. Their bones are lighter, sometimes nearly hollow, reducing the energy needed to move through cold water. Their muscles contract gently, avoiding bursts of speed that would demand more oxygen than their unique system can carry. Everything about them reflects patience, a calm acceptance of the environment that molded them. In the broader tapestry of Antarctic life, the icefish occupy a path carved by cold alone. While many species evolved in places where seasons brought warmth and sunlight, these fish grew in a world ruled by ice, darkness, and deep stillness. Their ancestors once swam in warmer seas, carrying hemoglobin like every other fish. But as Antarctica drifted south and the waters cooled, natural pressures began to shift. In the coldest regions, red blood was no longer essential. The environment itself carried enough oxygen to lighten the burden. Over long stretches of time, genes that once produced hemoglobin faded. In their place, new adaptations arose, small changes that allowed survival, where cold was no longer a challenge, but the defining force of life. There is a kind of beauty in the clarity of their blood, a transparency that mirrors the purity of the waters they inhabit. When one imagines the icefish drifting through the pale currents beneath an eternal winter, it becomes easy to see how the landscape shaped them. They are creatures built by cold, sculpted by an environment that rewarded stillness, steadiness, and silence. Their survival tells a story about evolution that is gentle yet profound. It shows that life can take paths that seem impossible at first glance, that nature can find ways to thrive even in places where warmth never arrives. The icefish move through the Antarctic waters with a quiet confidence, living proof that the cold does not always end life. Sometimes it transforms it. In the dim world beneath the continent, where the sea holds the memory of ancient climates and the pressure of drifting ice, these pale fish continue their slow rhythm. Their existence is a reminder that every extreme environment carries its own kind of possibility. In a place shaped entirely by cold, the icefish found a way to become something new. In the dim waters that surround Antarctica, where light fades long before it reaches the seafloor, shapes move with a patience found only in the coldest parts of the planet. Down here, the world is slow. Every current drifts as if reluctant to disturb the silence, and every creature seems shaped by the long, unbroken stillness of a frozen ocean. After meeting the icefish, pale and delicate in their clarity, the deeper waters offer another presence, one that seems almost unreal when first imagined. It is the giant Antarctic sea spider, a creature whose form looks as though it belongs to a different age of Earth. These sea spiders are not spiders in the way we know them on land. They are marine arthropods, distant relatives of crabs and other shelled creatures. Yet in the shadows of the Antarctic seafloor, their spindly legs stretch wide, sometimes reaching the size of a dinner plate. Their bodies remain small, no larger than the center of a palm, but their legs extend outward in long, thin arches that allow them to step lightly across the soft sediment. In still water, they resemble drifting fragments of ice crystals, delicate yet strangely enormous. Their size is possible because of the cold. In these near freezing waters, oxygen dissolves more easily than in warmer seas. The sea spiders do not carry this oxygen with the help of lungs or gills. Instead, they absorb it directly through the surfaces of their legs. Their long limbs act as quiet gateways where oxygen slips inward with little effort. The larger their surface area, the easier this becomes. As a result, the cold grants them the ability to grow into giants, not through strength or competition, but through a simple relationship with the chemistry of their world. They move very slowly. Every step is measured. Their legs lift and lower with the same rhythm as a falling snowflake, drifting down without hurry. This slow motion is not clumsiness. It is an adaptation to a place where energy must be spent carefully. Food is scarce in the dark beneath the ice, and speed offers little advantage. Instead, the sea spiders conserve their strength, allowing the cold water to support their bodies as they glide with near perfect balance along the sea floor. If one were to watch them long enough, the stillness around them would seem to deepen. Their bodies barely shift as they move. Only the legs, long and elegant, curl and unfold in steady arcs. In this dark environment, movement becomes a kind of whisper, a quiet gesture that carries the memory of ages spent surviving in slow motion. Despite their gentle appearance, sea spiders are hunters. Their prey is soft and often hidden. They feed on sponges, sea anemones, and small worm like organisms that cling to the undersides of rocks or nestle within patches of seafloor life. The sea spider feeds by extending a long, flexible mouthpart, almost like a delicate straw. With it, they pierce or probe their prey and draw out nutrients with silent persistence. Nothing dramatic occurs. There is no chase, no sudden strike. The predator meets the prey with the same calm pace that defines the rest of its life. In the deep Antarctic darkness, even feeding becomes an act shaped by patience. The sea spiders approach their food slowly, resting their legs lightly across the surfaces they explore. Their bodies bend with care. Their mouth parts move gently, testing textures that the eyes cannot see. Often the prey does not move at all. Sponges and similar creatures live simply, relying on the water around them to deliver sustenance. In this world, the boundary between predator and prey dissolves into a quiet exchange, one organism drawing energy from another with the softness of a drifting tide. Some species of sea spiders carry their young in clusters of eggs attached to their legs. The male protects them for weeks, sometimes months, walking through the dim water with the fragile spheres swaying beneath him. In the cold, development takes longer, so the father remains careful with every step. The eggs rise and fall gently as he moves, like lanterns carried by a traveler through a quiet submerged forest. As the spiders age, their legs grow longer with each molt. The cold supports this growth by slowing their metabolism, allowing them to reach sizes that would be impossible in warmer environments. Their organs stretch within their limbs, and the oxygen filled water passes across their surface in a slow chemical dance that keeps them alive. In a sense, the sea spiders are shaped from the water itself. They would not exist in this form if the ocean around Antarctica were even slightly warmer. The giant Antarctic sea spider stands as a reminder that size and speed are not always signs of dominance. Sometimes they are reflections of a world that asks for stillness rather than strength. In the deep water, where shadows blend with drifting snow-like particles and where time seems to lengthen, these creatures move with a grace that belongs uniquely to the polar seas. Their presence adds another layer to the silent ecosystems beneath the ice. Each long step marks a path through a landscape shaped by cold, pressure, and darkness. And in that path lies a story written over millions of years, a story carried not in sound or light, but in the slow, deliberate rhythm of survival at the very edge of the frozen world. Far below the drifting sea spiders, past the gentle plains of soft sediment and the quiet forests of sponges, the Antarctic Ocean becomes a place where even imagination seems to dim. Pressure rises with each meter. Light disappears. the water turns so cold and so dark that only the most patient creatures remain. Yet in this silent depth, a hunter moves with a presence so large and so rarely seen that it has become almost a myth. This is the colossal squid, a creature shaped by the deep itself, living in a realm where surprise is one of the last remaining elements of nature. The colossal squid is not often witnessed alive. Most of what we know comes from individuals brought up accidentally by fishing vessels or discovered drifting at the surface, their bodies softened by the long journey from the deep. Still, even these rare encounters reveal a shape made for darkness. Its mantle, smooth and firm, holds the quiet strength needed to live in a place where pressure presses inward from every side. Its tentacles stretch wide, trailing through water that has never known sunlight, and at the center of its face, resting beneath a curved head, sit the largest eyes of any creature known on Earth. Each eye is roughly the size of a dinner plate. If one were to imagine a glowing orb that could study the faintest flicker in the vast Antarctic dark, this would be it. The colossal squid does not rely on daylight. There is none at the depth it hunts. Instead, its eyes are tuned to the smallest of signals, the brief sparkle of bioluminescent organisms disturbed by movement, or the pale shimmer of a passing shape. In this way, the squid can sense a distant animal long before it draws near, following faint traces like distant lanterns that guide it across the deep. Its tentacles differ from those of its more familiar relative, the giant squid. Instead of suction cups, the colossal squid carries sharp hooks along the surface of its limbs. These hooks can swivel slightly, giving them the ability to grip prey with precision even when the water is cold and dense. Some are simple curved points, others have three fearsome prongs. They are not used with speed, but with quiet certainty. When the squid closes its limbs around a struggling prey, the hooks ensure that almost nothing can break free. For years, scientists wondered what a creature of this size could feed on so far below the surface, where food is scarce and energy must be conserved. The stomach contents of recovered individuals offered glimpses of their diet. Many contained fragments of large fish that drift through the deep, especially the Antarctic toothfish, a slow-moving predator in its own right. Other remains hinted at smaller squid species and occasionally soft-bodied organisms that wander the dim currents. The pattern suggested that the colossal squid chooses its prey carefully, capturing animals large enough to sustain its needs while avoiding wasteful chases in the dark. Its size, its eyes, and its hooks all point toward a life built around patience. Down here, quick bursts of movement are rare. The cold slows every heartbeat. The vastness of the deep sea spreads out the living world into thin strands. The colossal squid waits, sensing subtle movements, drifting just enough to close the distance. When a faint shimmer betrays the presence of a passing fish, the squid's limbs extend with a quiet force that belongs to the deep. There is no rush, only the certainty of a predator that has adapted to this world over countless generations. The Antarctic waters offer something that few other places can. They remain cold year-round, almost perfectly stable in temperature. This consistency creates an environment where metabolism slows to a gentle rhythm. The deep currents bring oxygen-rich water from across the planet, allowing animals like the colossal squid to rest and hunt without needing to stay constantly active. The darkness shields them from surface disturbances. The cold preserves energy. The quiet spreads across thousands of square kilometers, forming a realm where only creatures built for long patience can survive. Because of these conditions, the colossal squid has found a stronghold here. The Antarctic deep provides both the space and the stability needed for such a large animal to thrive. Other oceans hold squid species that grow to impressive sizes, but none match the colossal squid in bulk. Its body is heavier, more muscular, and suited for stillness under pressure. The Southern Ocean's deep basins give it room to drift, and the steady cold allows it to grow larger than any of its relatives. Though the colossal squid remains hidden from most human eyes, its story is written across the deep water of Antarctica. Every adaptation it carries, from its enormous eyes to its hooked tentacles, reflects the environment that shaped it. It is an apex predator not because of speed or ferocity, but because it has mastered the art of living in a world where light never arrives and where silence guides every movement. In this quiet, dark ocean, the colossal squid continues its slow journey through the depths, a creature built by time, cold, and the long patience of the Antarctic Sea. When the colossal squid retreats into the dark folds of the deep, the Antarctic world continues upward through layers of cold water that remain untouched by sunlight. Here, the ice shelf stretches across the sea like a vast floating ceiling. Its underside is uneven and ancient, a frozen landscape that moves so slowly that each shift feels like a sigh from another age. Beneath this ceiling, 600 meters below the surface, explorers once expected nothing more than drifting particles and the soft presence of microbes. Instead, during a series of hot water drilling missions, something surprising appeared in the beam of a small underwater camera. The drilling itself was simple in purpose. A stream of heated water carved a narrow path through the thick ice, clearing a tunnel wide enough for instruments to pass through. The water around the drill refroze quickly, turning the tunnel into a temporary window into a world sealed away for centuries. When the camera descended, its light spread through cold, clear water, gently revealing the shapes that drifted beneath the ice. At first, the feed showed what scientists had expected. Fine grains of organic debris floated like tiny flakes of ash, moved only by the slow pulse of distant currents. The seafloor lay far below, hidden in the dim beyond the camera's range. Then, without warning, a larger shape drifted past the lens. It was the size of a human hand, its legs folding and unfolding like soft paddles. Another followed, and then another, each moving with a quiet confidence in the cold water. These were amphipods, a type of crustacean usually no larger than a fingernail in most parts of the world. Here, though, they had grown to remarkable sizes. Their segmented bodies shone faintly in the artificial light, revealing delicate patterns and long, slender antennae that felt their way through the dark. They glided with a motion that seemed almost weightless, as if the cold water held them in a gentle embrace. The sight was so unexpected that the team observing the footage paused, watching these creatures move as calmly as if they belonged to a sunlit reef rather than a hidden world beneath kilometers of ice. Their presence raised a quiet question. How could such large animals survive in a place where energy is scarce and where the ocean receives almost no organic material from the surface? The answer lies in the subtle patterns of the under-ice ecosystem. Every fragment of detritus that falls from above, every drifting microbial mat, every trace of organic matter that rides a current from distant waters, eventually gathers into small pockets of life. Amphipods are well suited to these environments. They feed on whatever they can find, scraping food from the underside of ice, sifting through soft sediments, or consuming dead organisms that sink into the stillness. Their bodies have adapted to this world of limited resources. Cold water slows their metabolism to a gentle pace, allowing them to survive on less food than animals of similar size in warmer seas would require. The abundance of dissolved oxygen in Antarctic waters also encourages larger body sizes. Scientists call this polar gigantism, a phenomenon seen in many invertebrates living near the poles. In simple terms, the cold and oxygen rich environment allows some species to grow far larger than their temperate relatives. For amphipods, this size offers advantages. They can store more energy, travel longer distances in search of food, and withstand shifts in conditions that might harm smaller creatures. In the dim water, these large amphipods play an important role in the ecosystem. They act as recyclers, returning nutrients to the environment by breaking down organic material that most other creatures cannot reach. Their feeding keeps the balance of the under ice world steady, helping maintain the slow flow of nutrients that supports life beneath the shelf. They also serve as prey for larger animals, forming a link between microscopic life and the larger predators that wander the Antarctic depths. Watching them drift beneath the ice, one can imagine how their long antennae sweep gently across a world that rarely changes. The cold shapes every movement. Their legs paddle in slow strokes, carrying them across invisible trails left behind by currents. Occasionally, they curl their bodies and swim upward, as if testing the boundary where ice meets water. Then they sink again into the softness of the deep, returning to their quiet search for food. The discovery of these giant amphipods beneath 600 meters of ice showed that the Antarctic world remains full of surprises. Life continues in places where assumptions have long suggested inactivity. Instead of emptiness, there are creatures that have learned to grow large in stillness, to feed in scarcity, and to move with the calm rhythm of a world shaped entirely by cold. Their presence reminds us that ecosystems do not require sunlight to hold complexity. Even here, beneath a vast ceiling of ice, connections form, nutrients cycle, species adapt. The deep Antarctic Ocean holds its own kind of richness, carved not by warmth but by endurance. As these hand-sized amphipods drift through their quiet world, they embody the subtle strength of life that persists in the coldest corners of Earth. Far below the hand-sized amphipods and the drifting shadows of deeper hunters, the Antarctic waters continue to hold their own quiet mysteries. The underside of the sea ice is not smooth, but carved by slow movement and temperature changes, shaped by years of freezing and melting that leave delicate textures across its surface. In some places, strange rivers form within this ice, though they are not rivers of water as we usually understand them. They are streams of brine, colder and saltier than the ocean around them, and they sink with a purpose that gives rise to one of the most unusual structures in the polar sea. When seawater begins to freeze, the growing crystals push out salt, concentrating it into pockets within the ice. These pockets become reservoirs of supercooled brine, liquid that remains unfrozen even at temperatures where pure water would turn immediately to solid. Over time, the brine becomes dense, far heavier than the seawater below. Then, one quiet moment at a time, it escapes through small cracks in the ice and begins its descent. The sinking brine does not fall like rain or scatter like droplets. It pours downward in a steady curtain, turning the water around it so cold that any liquid it touches begins to freeze. The column forms an icy sheath as it moves, creating a hollow tube that extends ever deeper. This structure, growing downward from the ice ceiling, resembles a frozen stalactite. Scientists call it a brinicle, an ice finger shaped by the chemistry of salt and the bitter cold of the Antarctic Sea. A brinicle grows quickly. The cold brine flows through its center, freezing the surrounding water as it sinks. The tube expands and lengthens with surprising speed, sometimes reaching many meters toward the seafloor in only a few hours. Its walls thicken as the cold spreads outward, forming a delicate yet solid chamber of ice that looks almost fragile, though the water inside it continues to carve its hollow shape. As it touches the seafloor, The brinicle creates a pool of freezing water around its base. The cold spreads outward in a widening circle. Animals that wander too close are suddenly caught in a trap they cannot escape. Starfish, slow moving and unaware, sometimes crawl across the seafloor just as the freezing water reaches them. Their limbs stiffen, their bodies grow still. Small sea urchins, delicate in their own quiet ways, meet the same fate. The cold does not arrive with violence. It spreads like a soft tide, yet its effect is absolute. This gentle yet lethal touch is why some call the brinicle the ice stalactite of death. It is not a predator, nor does it choose its victims, but its formation creates a zone where few creatures can survive. The trapped animals become part of the frozen landscape, preserved briefly until currents shift and new water flows in to reshape the seafloor. Although the brinicle may seem like a destructive feature, it also supports life in hidden ways. Within the cold brine and along the icy walls of the tube, microbial communities gather. They thrive on chemical gradients created by the mixing of brine and seawater. In these gradients, minerals and salts shift in concentration, creating tiny zones where energy becomes available in ways unrelated to sunlight. Microbes use these gradients the way plants use sunlight, drawing energy from chemical change rather than from warm rays passing through the surface. These organisms are small, far too tiny to be seen by the camera lenses that recorded the amphipods and drifting shadows. Yet, they form a living film along the icy structures, transforming the brinicle into a quiet habitat. Where the cold restricts movement for larger creatures, the smallest organisms take advantage. They coat the interior walls with faint layers of life that grow slowly and steadily, following the rhythm of the brine flowing through the tube. The presence of these microbes reveals another side of this frozen world. Even in environments shaped by deep cold and chemical stress, life finds a way to build small communities. The brinicle becomes a home, a place where survival follows a path different from that of animals or fish. These microbial colonies support the broader ecosystem in subtle ways, releasing organic compounds that drift outward into the surrounding water. Other organisms may feed on those compounds, creating a tiny thread that binds the brinicle to the larger food web beneath the ice. As long as the brine continues to flow, the brinicle remains stable. When conditions shift and the movement slows, the ice finger begins to melt. The structure dissolves quietly into the sea, leaving only a faint memory of its shape and a patch of newly mixed water where the cold once spread. The seafloor recovers. The surviving creatures resume their slow movements across the sediment, and above them, within the ice, new pockets of brine wait for the right moment to descend again. In this hidden world, the brinicle stands as a reminder that even the simplest interactions of salt and temperature can create landscapes that seem almost otherworldly. It is a structure born from cold, guided by density, and inhabited by life too small to notice at first glance. Beneath the Antarctic ice, where time stretches and silence deepens, these frozen rivers continue their quiet descent, shaping the seafloor and supporting unseen communities in the dark. Beneath the quiet descent of brinicles and past the slow drifting of giant amphipods, another world waits in the shadows under the Antarctic ice. It is not a world defined by motion or sound. Instead, it glimmers with faint pulses of light, soft and momentary, like the flicker of distant stars reflected on deep water. These lights do not come from the surface. They come from the creatures that live in the coldest and darkest places on Earth, tiny beings that carry their own glow into the silence. The water beneath the ice shelves is vast. It stretches out beneath frozen ceilings that are sometimes hundreds of meters thick, creating long corridors of darkness where sunlight has never entered. In this place, eyes would be useless for most animals. Shapes fade, boundaries dissolve, yet even here, light finds a way. Small drifting organisms, no larger than grains of sand or threads of jelly, release brief sparks of blue or green whenever something brushes past them. These are bioluminescent plankton. They drift freely with the currents, carried along in slow spiraling patterns beneath the ice. Their bodies contain intricate chemical systems that can create light through reactions between stored molecules. In warmer oceans, these reactions are often triggered by waves or predators, turning entire beaches into glowing blue shores on certain nights. In Antarctica, the cold slows everything. The glow becomes gentler, more subtle, often appearing as faint halos rather than bright flashes. Still, the darkness around them makes even the smallest glimmer stand out. When a tiny disturbance ripples through the water, a few plankton respond with a soft flash that spreads like a whisper across the current. Another pulse might follow from nearby organisms, forming a slow-moving cloud of light that drifts for a moment and then fades. The effect is delicate, like watching constellations form and dissolve inside the sea. The chemical process behind their glow is shaped by the extreme cold. Every reaction here happens at a slower pace, almost as if time stretches out around the plankton. The molecules used to produce light must be specially adapted to function in these temperatures. If they were the same as those found in warmer waters, the cold would weaken or stop the reaction. Instead, Antarctic bioluminescent organisms carry versions of these chemicals that remain flexible in frigid water. Their glow may be softer, but it remains dependable, a quiet tool that has endured through countless generations. Bioluminescence becomes especially important in the absolute darkness beneath the shelves. Here, it serves as a signal, a small burst of communication in a world without sunlight. Some plankton release light when attacked, hoping to startle a predator or draw attention to a larger animal that might scare it away. Others glow in gentle pulses during certain stages of their life cycle, perhaps attracting mates or coordinating movement within drifting groups. Even though these signals are brief, they carry meaning. Light becomes a language shaped by need and shaped by cold. Larger creatures take advantage of this glow as well. Some fish and invertebrates move slowly beneath the ice, following faint trails left by glowing plankton. To them, bioluminescence marks the presence of prey or offers clues about the path of a drifting current. In a place where vision is limited, even the smallest shimmer becomes a guide. The glow of plankton creates a soft map of the surrounding water, constantly shifting but always offering hints about nearby life. For the plankton themselves, glowing can mean survival. In warmer seas, bioluminescence sometimes draws predators closer. In Antarctica, the pattern shifts. Many predators in these dark waters hunt by sensing movement, not by sight. A sudden flash can confuse them, causing the predator to lose track of its target. In this way, light becomes a shield rather than a lure. The cold water also slows attacking animals, giving the plankton a better chance to slip away while the glow fades. The glow has another subtle benefit. In the deep Antarctic waters, energy is scarce. Small organisms rely on drifting organic material to survive, and competition can be intense. Bioluminescence may help some species gather around nutrient-rich pockets, following faint signals that guide them toward areas where food is more abundant. Light becomes a compass, pointing toward opportunity. Sometimes the glowing plankton gather in thin layers near the underside of the ice. When this happens, the world beneath the shelf takes on a quiet beauty. Soft halos drift upward like glowing snow. A distant shape moving through the water might disturb these layers, creating a trail of illumination that slowly spirals toward the surface. For a moment, the darkness breathes with scattered light, then the cold folds around it again. Though each glowing organism is small, together they shape the rhythm of life beneath the ice. They offer signals, warnings, guides, and brief windows of visibility in a world ruled by darkness. They are reminders that even in the coldest corners of the planet, life carries its own light, shaped not by the sun, but by deep time and quiet need. In this hidden ocean, the creatures that glow do not brighten the landscape in any grand way. Their light is soft, almost hesitant, yet perfectly suited to their world. It drifts slowly through the darkness, offering tiny sparks of meaning beneath the vast, frozen ceiling of Antarctica. Far beneath the glowing trails of drifting plankton, the Antarctic waters widen into long, dark domains where even chemical light becomes rare. The cold here has a stillness deeper than silence, and the currents move with the slow patience of a resting planet. In this quiet space, shapes glide that seem almost more water than animal. Their bodies are soft, transparent, and nearly invisible until a faint shimmer catches the light from a descending probe or the gentle glow of nearby plankton. These are the jellyfish that inhabit the hidden seas beneath Antarctica's ice, creatures so delicate that the water itself appears to cradle them. They drift through the black seawater with a grace that belongs to places untouched by storms or sunlight. Their bodies pulse in slow, rhythmic waves, pushing them forward with the gentlest of motions. Nothing about their movement is hurried. The cold demands careful use of energy, and the jellyfish have mastered the art of moving with minimal effort. Their gelatinous forms allow them to float almost effortlessly, rising and sinking with minor changes in buoyancy. Only small contractions of their bell-shaped bodies guide them through the stillness. This lifestyle suits the deep Antarctic Ocean well. Here, nutrients are scarce, arriving only as faint traces from distant waters or as soft particles drifting downward from the ice above. Many animals cannot survive in such limited conditions, but jellyfish thrive. Their bodies are mostly water, requiring little fuel to maintain. Their slow metabolism keeps their needs small. They drift, they pulse, they wait. In a world where patience is one of the few reliable strategies, they become the quiet rulers of the dark. Because light never reaches these waters, jellyfish cannot rely on vision. Instead, they sense the world through gentle vibrations, chemical traces, and subtle shifts in the water around them. Every movement creates a ripple. Every living creature leaves behind a faint chemical signature. The jellyfish detect these patterns with remarkable sensitivity. Their tentacles, trailing like thin threads, pick up the slightest change in pressure, allowing them to recognize when something approaches from any direction. Predators moving through the darkness often disturb the water with their size or speed. A jellyfish feels this long before the hunter arrives. Sometimes the jelly will fold inward, shrinking its profile into a smaller shape. Sometimes it glides downward, sinking toward deeper layers where the disturbance cannot reach. Other times it simply drifts away, letting the current carry it to safety. These responses require almost no energy, which is essential in a place where food is rare and every movement matters. When the jellyfish seek prey, the same sensitivity guides them. Tiny crustaceans, small worms, and drifting organic particles make up their diet. Many of these are nearly invisible even in the faint glow of bioluminescent light, yet they give themselves away through motion, a slight vibration, a small disturbance, a sudden shift in the water's density. The jellyfish detect these cues and extend their tentacles with gentle precision. Some species carry stinging cells that paralyze prey almost instantly, while others rely on sticky surfaces that trap anything brushing against them. The prey is drawn inward to the jelly's central mouth, consumed slowly, and transformed into the energy that allows the creature to continue its drifting path. Despite their fragile appearance, jellyfish dominate many parts of the under-ice ecosystem. Their ability to survive on minimal nutrients gives them an advantage over animals that require more energy. When food is scarce, jellyfish endure. When temperatures fall lower than most creatures can tolerate, jellyfish continue their slow rhythm. Their bodies can withstand pressures that would crush many organisms, and they can adjust their buoyancy with ease, allowing them to travel across wide layers of the water column. In some regions beneath the ice shelves, scientists have observed entire clouds of jellyfish drifting together. Each one remains quiet, pulsing with soft movements, creating a gentle dance of translucent shapes. These gatherings are not the frenzied swarms seen in warmer oceans. They are calm, widely spaced formations, like drifting galaxies slowly rotating in the dark. Their presence shapes the flow of nutrients, their tentacles collecting particles that would otherwise sink untouched into the deep. The transparency of their bodies plays another role. In a world where nearly every creature has evolved to sense motion rather than sight, transparency minimizes disturbance. A clear body moves cleanly through the water, creating fewer ripples than a solid one. The jellyfish become part of the water around them, merging with it rather than cutting through it. This subtle adaptation adds to their ability to survive in an ecosystem where any unnecessary movement might waste precious energy. Some species even possess faint, low-energy forms of bioluminescence. These glows are softer than those of the plankton above, sometimes appearing only when the jellyfish is touched or alarmed. The light may startle a predator or create a brief signal that confuses an approaching threat. Other species show no glow at all, choosing silence in every sense, drifting unseen through a world that depends on subtlety. As the jellyfish move beneath the Antarctic ice, their presence becomes part of the slow rhythm that defines these waters. They fill spaces where light cannot guide life. They create pathways of energy in an ecosystem shaped by scarcity. Their bodies, simple yet ancient in design, remind us that survival can take many forms, and that some of the most delicate creatures hold a profound place in the structure of deep ocean worlds. Here in the quiet beneath the ice, they drift as if carried by time itself, transparent guardians of a realm shaped by cold, darkness, and patience. Far below the drifting jellyfish, in waters where the cold settles into every particle of the sea, another creature moves with a steadiness that belongs only to the deep Antarctic world. It does not glow like the plankton above. It does not drift with the softness of jellies or glide with the ghost-like reach of amphipods. Instead, it swims with slow, deliberate motions, each movement measured against the stillness of its home. This is the Antarctic toothfish, a silent hunter that has shaped the rhythm of life in these frigid waters for far longer than humans have known the continent existed. The toothfish is large, far larger than most fish that live in such cold environments. Some individuals grow longer than an adult human, their bodies thick and strong, built for endurance more than speed. Their skin is pale, holding a cold shimmer that mimics the water around them. Their eyes are dark and steady, adapted to a world where light is scarce and where shapes must often be sensed rather than seen. Despite their size, toothfish hunt slowly. They do not chase prey with bursts of speed or flashing strikes. Instead, they move at a gentle pace, letting their bodies blend into the dim water. A patient drift becomes their greatest tool. In these depths, where life moves cautiously, Sudden motion draws attention. The toothfish avoids that. It advances with a steady confidence, conserving its energy for the rare moments when precision matters. Their prey includes smaller fish, cephalopods, and sometimes drifting invertebrates. Because the cold slows everything, including metabolism, prey animals often move with predictable patterns. A toothfish can approach calmly, align itself, and open its mouth with a smooth and intentional motion. The capture is quiet, a simple exchange of movement and stillness. Little is wasted. Every act of feeding is shaped by the same careful rhythm that governs the rest of its life. Deep within its tissues, the toothfish carries antifreeze proteins, similar to those found in other Antarctic species but uniquely suited to its large body. These proteins wind through its blood and cells, preventing the formation of ice crystals when the surrounding water falls below the freezing point of pure water. Without these molecules, the cold would seize the fish from within, turning fluid into solid. With them, the toothfish remains flexible and alive, even in temperatures that feel impossible for vertebrates. The presence of antifreeze proteins also allows the toothfish to range across wide depths. It can swim near the underside of ice shelves or descend into deeper basins where temperatures drop even further. In these places, pressure grows heavy and food becomes scarce, but the toothfish persists. Its metabolism responds to the cold by slowing, sometimes to an extent that would be dangerous in warmer seas. Here, however, the slowness becomes a strength. It reduces the need for frequent feeding. It prolongs lifespan. It shapes the fish into a creature that lives in tune with the gentle pace of Antarctica itself. Toothfish are known to live for many decades. Some individuals approach ages that rival long-lived land animals like elephants. Their slow growth and steady movements reflect the environment that raised them. They grow gradually, layer by layer, adding to their strength with time rather than with rapid bursts of youth. This longevity makes them central figures in the deep ecosystem. A single toothfish may live long enough to witness shifts in ice shelves, changes in currents, or subtle adjustments in temperature that unfold across generations. Because of their size and abundance, toothfish hold an important place in the Antarctic food web. They sit near the higher levels of the underwater hierarchy, feeding on smaller animals while also serving as prey for larger ones. The colossal squid, the same shadowed hunter that drifts through the darkest depths, often carries scars that match the teeth of a toothfish. Scientists have found toothfish remains in the stomachs of captured squid, revealing a predator relationship shaped by patience and cold. Seals, especially Antarctic species that hunt in deep waters, rely heavily on toothfish for sustenance. Their dives carry them through the shadowed regions where toothfish swim, and their powerful bodies allow them to pursue the slower moving fish with bursts of speed rarely seen in these waters. A single hunt can support a seal for days, linking the quiet endurance of the toothfish to the survival of creatures that move with far greater force. Even the structure of the ecosystem depends on toothfish. When they feed, they redistribute nutrients through different layers of the ocean. When they excrete waste, they release organic material that drifting plankton or small invertebrates may consume. When they die, their bodies sink into the deep, becoming rich sources of energy for bottom-dwelling species. In this way, the toothfish forms a bridge between the upper and lower regions of the under-ice world, connecting distant pockets of life through subtle exchanges. Despite their importance, toothfish remain elusive. They do not gather in large schools or rise to the surface in great numbers. They live in darkness, moving through waters that humans have explored only briefly. Most of what we know about them comes from careful studies of captured individuals and from glimpses recorded by deep-sea cameras. Yet their presence is felt throughout the Antarctic ecosystem. They carry the cold in their bones and the patience of the dark ocean in their movements. They show how life adapts not only to survive, but to thrive in environments that appear inhospitable. The toothfish, with its slow pulse and steady gaze, is a quiet guardian of the deep, a reminder that even the harshest environments can shape creatures of remarkable resilience. In the still waters beneath the ice, where every motion feels like a whisper from another world, the toothfish swims with a calm that belongs solely to Antarctica. Beneath the drifting path of the toothfish, and far below the silent pulse of jellyfish, the Antarctic continent hides a deeper mystery still. It lies not in the open sea, but in the solid ground of the continent itself, where thick ice rests upon valleys carved long before humans appeared. Beneath this ice, sealed beneath thousands of meters of frozen weight, are lakes that have not seen the sky for millions of years. They form a hidden network of dark, ancient waters, known as subglacial lakes, places where life endures without sunlight, without warmth, and without any of the comforts that shape ecosystems elsewhere on Earth. Among these lakes, a few names echo through scientific history. Lake Vostok, the largest, stretches across an area comparable to a small sea, yet it remains sealed beneath ice thicker than any human-made structure. Lake Whillans lies closer to the coast, quietly pulsing as it fills and drains through subglacial rivers that flow beneath the ice sheet. Lake Ellsworth rests within a deep valley, isolated by ice walls older than the earliest human cultures. Each lake holds its own story, shaped by pressure, darkness, and chemistry. These lakes exist because the weight of the ice above them generates heat through slow, constant pressure. The ice insulates the land below, trapping geothermal warmth that rises from the crust. Over time, ice at the bottom melts into liquid water, gathering in old basins and forming the hidden lakes. The pressure here is immense, enough to compress the water into a dense and cold, yet stable form. No sunlight penetrates these depths. The lakes have lived in darkness for so long that their ecosystems evolved entirely without photosynthesis. The chemical makeup of these waters reflects their isolation. The lake bottoms often contain sediments rich in minerals released from ancient rocks. Because sunlight cannot reach the lakes, the organisms living here rely on these minerals for energy. They use chemical reactions to survive, breaking down compounds that seep slowly from the underlying bedrock. This process, called chemosynthesis, functions like a silent lantern that guides life through complete darkness. What sunlight does for forests and oceans above, rock-derived energy does for life below the ice. In Lake Whillans, tiny bacteria feed on minerals containing iron and sulfur. These reactions release small amounts of energy, enough to support colonies of microbial life that drift through the water or cling to sediments. Lake Vostok, with its immense size and long isolation, may hold even more complex chemical gradients. Samples taken from the ice above the lake hint at diverse microbial communities that have spent ages adapting to the unique chemistry of their hidden world. Lake Ellsworth, though smaller, shows signs of similar processes, with water samples revealing cells that have persisted for untold generations without ever touching the open air. The pressure within these lakes is intense, shaped not only by the ice above but by the depth of the basins themselves. Microbes here live in conditions so dense that their cell walls have evolved unusual structures, allowing them to withstand forces that would crush many surface-dwelling organisms. Their enzymes, the molecules that fuel life's reactions, remain functional at temperatures near freezing. Their metabolisms, slowed by the cold, allow them to survive on tiny amounts of energy. In some cases, a single cell division may take years. These organisms do not form large, visible shapes like the creatures in the open sea. Instead, they exist as threads of life woven through water and sediment. Yet their resilience reveals something profound. They show that ecosystems can exist even in total darkness, powered not by the sun, but by the chemistry of Earth itself. They show that life can persist quietly, shaping itself around constraints that seem impossible. Evidence of unique microbial lineages continues to emerge from samples taken from these lakes. Many of these microbes are unlike anything found on the surface. Their genetic signatures carry hints of adaptations that evolved in complete isolation. Some may represent ancient lineages preserved by the cold and cut off from the rest of the biosphere. Others may have developed entirely new strategies for survival, shaped by chemical gradients and slow moving currents beneath the ice. When scientists study these organisms, they often speak of the lakes not simply as bodies of water but as separate worlds. Each lake forms a complete system, with its own sources of energy, its own nutrient cycles, and its own evolutionary histories. In Lake Vostok, for instance, the interaction between mineral rich sediments and slowly circulating water may create chemical layers that support different microbial communities. In Lake Whillans, the flow of water through subglacial rivers introduces new materials, allowing microbes to process a wider range of compounds. Lake Ellsworth remains a mystery still, but the few samples obtained suggest it too supports life adapted to long stretches of isolation. The stillness within these lakes does not indicate emptiness. Instead, it reflects a balance that has held for ages. The microbes move slowly, living at the edge of what is chemically possible, yet they persist. Their presence links the living world to the deep geological history of Antarctica, connecting the cold of the present to the warm landscapes that once existed long before ice covered the continent. In these subglacial waters, time feels stretched. Evolution moves at a patient pace. Life follows paths carved by darkness and pressure. As we explore these hidden lakes, we discover not only new forms of life, but new ways of understanding what it means to inhabit a planet shaped by slow, powerful forces. Here, beneath the thick ice, ecosystems survive without sunlight, nourished instead by the quiet chemistry of ancient rocks. Beneath the great shelves of Antarctic ice, where subglacial lakes keep their long silence and life survives on the chemistry of stone, another form of community grows. It does not move with the drifting grace of jellyfish or glide along with the quiet purpose of amphipods. It does not hunt like the toothfish or rise in sudden flashes of bioluminescent light. Instead, it rests upon the seafloor in thin, patient layers, building its presence grain by grain over centuries. These are microbial mats, slow-growing sheets of bacteria that form living carpets across the dark world beneath Antarctica. At first glance, they appear simple, like soft films of color resting upon sediment. They cling to rocks, spread across old mineral fragments, or shape themselves into small ridges that follow the contours of the seabed. But each sheet contains countless cells, arranged in delicate structures that have taken years, sometimes centuries, to rise into visible form. They live in conditions harsher than nearly any found on the surface of Earth, yet they persist with a steadiness that speaks to the deep resilience of life. These mats do not rely on sunlight. The ice above them stretches for hundreds of meters, blocking every hint of day. The bacteria within the mats have evolved to survive through chemosynthesis, a process that allows them to draw energy from chemical reactions rather than light. They feed on minerals released from rocks, or on compounds drifting in from distant volcanic seeps, or on the slow decay of organic matter that settles through the water. Chemosynthesis is gentle but constant. It does not produce the bursts of energy that sunlight drives in the open ocean. Instead, it works like a low burning flame, releasing just enough power to sustain life in slow motion. The bacteria capture this energy and share it across their communities, forming layers in which each stratum depends on the ones above and below. Some layers break down sulfur compounds, others process iron, still others specialize in recycling organic particles. Together, they create a stable and self contained ecosystem that can survive where most other organisms cannot. Under the ice, where nutrients are scarce and movement is slow, these microbial mats play a vital role. They take scattered materials and weave them back into the food web. When organic debris drifts downward from higher waters, the mats gently absorb it. When minerals seep from the seabed, they transform those elements into forms that other organisms can use. Even creatures as small as amphipods or as large as bottom-dwelling fish rely on the nutrients the mats release. In this way, the mats act not only as living carpets, but as quiet engines of renewal. Some mats also form near the edges of subglacial lakes, where thin channels connect lake water with the open sea. Here, the mats capture chemical signatures from ancient sediments, transforming minerals that may have remained untouched for millions of years. Their presence helps scientists understand how life might have existed on the early Earth when light was scarce and energy came mostly from the warm breath of the planet itself. What makes these microbial colonies especially remarkable is their resilience. The cold slows their metabolism to such an extent that they can survive long periods without fresh nutrients. If conditions change, they retreat into a dormant state, waiting calmly until the environment becomes favorable again. Some mats have likely existed in the same places since before human civilizations rose and fell. Layer by layer, they recorded shifts in temperature, in chemical supply, in the slow carving of the ice above them. Their resilience also shows in their ability to rebuild. If part of a mat is disturbed by a shifting current or a passing animal, the remaining cells reorganize themselves. They expand gently outward. They form new layers. Over time, the damaged area heals, returning to its earlier structure. This regrowth happens slowly, but time passes differently. In the cold, a year, a decade, even a century becomes a quiet moment in the rhythm of their existence. Because these mats operate on such long time scales, they reveal the continuity of life in a place shaped by isolation. They show that ecosystems do not need rapid growth or abundant energy to flourish. They need stability, patience, and the ability to adapt to what the Earth provides. The Antarctic mats accept the darkness as their foundation. They accept the cold. They accept the slow drift of nutrients. In return, they carve out a place for life in conditions that would seem impossible. Sometimes researchers collect samples from these mats to study their structure. Under a microscope, each sample reveals a mosaic of bacteria, arranged in patterns as intricate as woven cloth. The layers stack like pages in a book, each one telling a story of chemical change, temperature, and time. Some cells belong to lineages older than any human society, shaped by countless generations spent beneath ice and silence. Others represent more recent arrivals, drifting in from the surrounding waters and settling into the mat's collective life. As the mats grow, they influence the chemistry of the entire region around them. They remove toxins, they stabilize sediments, they release compounds that feed other microorganisms. Their presence allows complex ecosystems to form above them, even in a world where sunlight never shines. In this hidden realm, they act as the foundation for life, anchoring the energy cycle in a place that has remained cold and dark for ages. Under the Antarctic ice, where every organism moves slowly and survival depends on quiet adaptation, the microbial mats sit calmly on the seabed. They are reminders that life can endure wherever it finds even the faintest source of energy. They show us that resilience does not always roar. Sometimes it grows in thin, patient sheets across the floor of a frozen ocean, older than civilization, yet still alive with possibility. Far beneath the slow growing microbial mats, and deeper still than the drifting layers of ancient sediments, a different kind of life waits in the shadows. It does not drift through the water or cling to the underside of ice shelves. It does not glow or move or pulse. Instead, it lives directly within the rocks beneath Antarctica, hidden in cracks and pores that have been sealed away from sunlight for longer than the ice above has existed. These organisms are lithotrophs, creatures that feed not on organic material or sunlight, but on the chemistry of stone itself. Their world is silent and still. The bedrock beneath the Antarctic continent is ancient, forged in eras when the planet was warmer and seas covered land now buried under kilometers of ice. Over time, these rocks cracked under pressure, releasing minerals slowly as they interacted with water. In these dark spaces, where heat from the Earth's interior rises quietly and water seeps like a thin veil through the ground, lithotrophs found their home. Lithotrophs survive by using inorganic chemical reactions as their source of energy. They feed on iron, sulfur, hydrogen, or other minerals released from the rock. To them, a grain of sandstone or basalt holds the same potential energy that sunlight offers the forests of the surface. Their lives unfold in slow, measured rhythms, drawing strength not from warmth or movement, but from the steady release of electrons in chemical reactions that unfold molecule by molecule. To understand their world, it helps to imagine a space where darkness is absolute. No shape, no shadow, no glimmer of bioluminescence. The only movement is the slow seep of mineral-rich water filtering through rock channels, carrying the faint chemical ingredients that sustain these microorganisms. The cells themselves exist in clusters so small that billions could fit within the tip of a needle, yet their presence carries meaning far larger than their size suggests. These organisms offer a quiet glimpse into Earth's deep past. Long before plants filled the land with green, and long before animals roamed oceans or walked across continents, the planet was a place without sunlight-driven ecosystems. Early Earth was warm in some regions and frozen in others, but much of its surface remained inhospitable to life as we know it. Yet within the rocks and near hydrothermal vents, organisms similar to lithotrophs may have thrived, using chemical reactions to survive in a world where sunlight struggled to reach new land masses or shallow seas. Their existence beneath Antarctica hints at how early life might have begun. They show that life does not require open oceans or bright skies. It can begin in darkness, drawing strength from the structure of the planet itself. In this way, lithotrophs serve as living echoes of Earth's earliest biosphere. They reveal that life's foundation may rest not on sunlight, but on chemistry. The survival strategies of lithotrophs are especially remarkable in a place like Antarctica, where organic nutrients are scarce. Many organisms depend on the slow rain of organic particles drifting downward from the upper layers of the ocean. But beneath the continental ice sheet, far from the sea and deeper than even the toothfish roam, this rain does not fall. Lithotrophs instead build their communities around the energy stored in minerals. They turn the Earth's crust into a source of nourishment, reconstructing chemical compounds and releasing energy as they break down elements locked within the rock. Their metabolism runs slowly. A single cell may divide only once in many years, Yet slowness is not a weakness here. It is a strategy shaped by cold and scarcity. By stretching their lifespans across long spans of time, they avoid the need for frequent energy intake. They endure changes in groundwater flow, in mineral composition, and in pressure that would challenge more delicate organisms. Researchers often look to these lithotrophic communities when considering the possibility of life beyond Earth. On moons like Europa or Enceladus, oceans rest beneath icy shells thicker than the Antarctic ice sheet. Sunlight cannot reach them. Yet volcanic activity and chemical reactions within the rocky interior may release minerals into the water, creating conditions similar to those beneath Antarctica. In these distant worlds, life could begin not with sunlight but with stone. Lithotrophs show us how such ecosystems could form, how they might persist, and how they might leave subtle signatures for future explorers to discover. Even Mars, with its ancient valleys and hints of past water flow, invites comparison. If water once seeped into fractured rocks, similar organisms might have lived there in the distant past, tucked within mineral-rich environments similar to those beneath Antarctic ice. Lithotrophs help scientists imagine these possibilities with practical clarity. Their survival proves that life can exist where organic nutrients are absent, where light is absent, and where energy comes only from the planet's slow breathing. Though invisible to the naked eye, lithotrophs play a quiet role in shaping Antarctic landscapes. They alter the minerals they feed upon, leaving behind faint chemical signatures that scientists can detect. They influence the groundwater that moves beneath the ice. They support tiny microbial communities that rely on the compounds they release. In this way, they contribute to the deep ecosystem just as profoundly as the fish, jellies, and mats above them. Lithotrophs demonstrate that life's boundaries are far wider than what we see at the surface. In absolute darkness, under immense pressure, sustained only by stone and chemistry, they thrive. They whisper of life's deep history and of possibilities yet to be discovered in worlds distant from our own. Here, beneath Antarctica, they continue their slow work, shaping life where even the sun cannot reach. Beneath the thick Antarctic ice, where sunlight does not reach and seasons pass without a single glimmer of day, life continues in ways that seem almost impossible. Here in the stillness, where lakes hide beneath kilometers of frozen weight and seawater flows beneath towering ice shelves, an entire food web exists. It is not built on green plants or drifting algae. It is not fed by warmth or nourished by light. Instead, it follows the quiet movement of chemicals, minerals, and the slow recycling of organic matter across generations. In most of the world, energy begins with sunlight. Plants and algae capture it, animals feed on them, and predators feed on the animals. But beneath Antarctic ice, the typical order collapses. The foundation of life shifts from light to chemistry. Microbial mats use the minerals around them. Lithotrophs feed on the stone beneath the continent. Other bacteria gather energy from chemical reactions in water that moves through the subglacial world. These tiny organisms, so small they seem like scattered grains of dust under a microscope, become the base of the entire system. Even though they are invisible to the eye, their impact spreads through every part of the under-ice world. When they grow, their cells form the first building blocks of the food chain. When they die, they release nutrients that drift into the water or settle onto the seafloor. Every layer of life begins with their slow and steady work. Above them, slightly larger creatures wait for these traces of energy. Tiny filter feeders collect drifting particles, drawing nourishment from material that may have originated many years or even centuries earlier. Some crustaceans feed on bacteria directly, scraping mats off rocks or stirring the sediment to release trapped nutrients. Their movements are slow, shaped by the cold and by the scarcity of food, yet they hold an important place in the cycle. They transform microscopic energy into forms that larger animals can recognize. Predators in this world move with equal patience. There are no fast chases or bright flashes. Every motion wastes energy, so the rhythm of predator and prey becomes almost gentle. Amphipods, with their long limbs and careful strokes, drift through the water, searching for small organisms or fragments of decayed matter. Fish glide with steady precision, feeding on crustaceans or scavenging from the seafloor. Jellyfish pulse softly, capturing whatever brushes against their tentacles. Even the colossal squid, far below, follows this slow rhythm, choosing prey that offer enough nourishment to justify the effort. Nothing is wasted here. When a creature dies, its body sinks into the dark water or collapses gently onto the sediment. Microbes gather around it, breaking it down into smaller pieces. Crustaceans approach next, feeding on what the bacteria leave behind. Their waste drifts away, becoming nutrients for microbial mats. Over time, the organic material becomes part of the chemical cycles that support lithotrophs and other bacteria. In this way, one life sustains another, even if they never directly meet. This recycling can span several generations. The matter from a single fish might nourish countless organisms across decades. The cold slows decay, stretching the timeline and allowing every piece of organic material to circulate through the ecosystem with remarkable efficiency. It is a quiet process, unhurried, shaped by the pace of the environment itself. What makes this world particularly surprising is its complexity. Scientists once believed that such extreme environments would host only a few simple organisms. The lack of sunlight, the constant cold, and the high pressure all seemed to limit what life could achieve. Yet the more researchers explore, the more they find that life beneath the ice is interconnected in ways as intricate as any sunlit ecosystem. Some bacteria specialize in breaking down sulfur, iron, or methane. Others rely on compounds that drift in from volcanic vents far below. Some organisms feed almost exclusively on microbial mats. Others use chemical cues to locate organic fragments in the dark. Even light itself plays a small role. Bioluminescent plankton glow occasionally, helping predators sense movement or signaling mates in the dark. The food web stretches from the smallest microbe to the largest toothfish or squid. It spans thousands of meters of water and reaches into the rocks themselves. It links creatures living beneath the ice shelf to those swimming through the deep sea bordering Antarctica. Each organism fills a distinct place, shaped by the limits and opportunities of an environment that appears empty at first glance but holds a quiet abundance. What is most striking is how slowly this world moves. Every part of the food web hums with the same soft tempo. Predator and prey respond to one another without rush. Microbes grow slowly, releasing energy over years. Fish and invertebrates take decades to reach full size. Even the recycling of a single fallen organism can unfold across long stretches of time. This slowness does not weaken the ecosystem, it strengthens it. It allows each piece of organic matter to be used fully. It lets creatures survive long periods of scarcity. It builds a stability that mirrors the ice above, steady, patient, and enduring. In the still world beneath Antarctica, the food web that should not exist thrives in its own quiet way. It shows that life can follow paths far different from those shaped by the sun, and that even in the deepest cold, the planet finds ways to weave connections that endure across generations. Far beneath the wide shelves of Antarctic ice, beyond the drifting food webs and hidden lakes, the seafloor opens into landscapes that few imagined could exist in such darkness. Here, the cold is constant, and the water moves with a softness that feels almost timeless. No sunlight reaches these depths, not even the faint glow that filters through thin ice in northern seas. Yet, resting gently on the seabed, there are forests, not forests of wood or leaves, but forests of sponges, rising from the floor in shapes that look like frozen bouquets or the trunks of pale, silent trees. These sponge colonies are enormous. Some individuals stand taller than a person's waist, their bodies forming thick walls of soft, porous material. Others stretch outward in wide clusters, covering large areas of seafloor like slow growing fields. Each sponge grows at a pace shaped by the deep cold. Instead of racing through life, they build themselves one tiny layer at a time, adding mere millimeters over the span of years. It is not uncommon for these sponges to be centuries old. Some may have begun their slow rise when ancient civilizations on the surface were taking their first steps into history. The darkness does not weaken them, it simply changes the rules. Since the sponges cannot rely on sunlight, they depend on tiny particles drifting through the water. But even this is not the full story, because many of these sponges carry hidden allies within their bodies. Inside their soft tissues live microbial symbionts, microscopic companions that act like internal power plants. These microbes convert dissolved chemical compounds into energy, feeding the sponge from within. It is a quiet partnership. The sponge shelters the microbes, offering them a stable home and a constant flow of water through its internal channels. The microbes, in return, process nutrients that the sponge could not use on its own. They break apart chemical bonds in the water, gathering energy from reactions that occur even at freezing temperatures. This energy flows into the sponge's tissues, supporting its slow growth and keeping the colony alive across centuries. This partnership allows the sponge forests to survive in conditions that would be impossible for most creatures. Organic material arrives only in faint traces, falling gently from the waters above or drifting in from distant parts of the under-ice world. The sponges filter it patiently, capturing even the smallest fragments. Meanwhile, their microbial partners continue their steady chemical work, ensuring that the sponge survives even during long stretches when food is scarce. The stability of the cold plays a crucial role. Water temperatures beneath the ice shelves remain almost constant year after year, never warming, never cooling beyond a narrow range. In this still environment, life does not need to rush. Growth becomes a slow unfolding, shaped by time rather than competition. A sponge may take a human lifetime to reach a size that other creatures achieve in a few years, yet the slow pace brings a kind of resilience. The colony remains stable through centuries of subtle shifts in the ice above. Because these sponges live for so long, they act like living records of the past. Their tissues hold chemical signatures that reflect the conditions of the water around them. Layers within their bodies capture traces of minerals and elements that drifted through their environment centuries before. Scientists studying these colonies have found hints that past climates left marks within the sponges, revealing changes in water circulation, nutrient flow, and even the movement of ice shelves. Some sponge colonies rest in places that were once open ocean before the ice advanced across them. Their presence there suggests that the water beneath the shelves was once connected to brighter, warmer regions. Over thousands of years, as ice thickened and sealed off the area, the sponges remained. They adapted, slowed their growth, and continued their quiet existence in an environment transformed around them. In other regions, where the ice has remained stable for long stretches of time, Sponge forests have grown into vast communities. These groups form complex habitats. Small crustaceans weave through the sponge branches. Tiny worms build tunnels in the sediment below. Microbes drift in trails through the water, feeding on nutrients released by the sponges or their internal symbionts. The forest becomes a structure upon which entire miniature ecosystems depend. Its stillness supports a delicate balance of life, each part intertwined in ways that can be seen only with close, patient observation. The discovery of these sponge forests surprised many researchers. No one expected such abundance in a place without sunlight, where nutrients are scarce and temperatures hover just above freezing. Yet the sponges rise from the seafloor like monuments to endurance, shaped by simple needs and long spans of time. They demonstrate that ecosystems can flourish even in the quietest corners of Earth, given stability and a steady source of chemical energy. Their presence also offers clues about the future of Antarctica's hidden waters. If ice shelves retreat or currents shift, these forests will feel the change long before humans sense it on the surface. Their growth patterns, their microbial partnerships, and the chemical traces within their tissues will all respond to the smallest variations in their environment. For now, they remain in their silent world, rising gently through darkness, shaped by patience and cold. They are the forests of the deep Antarctic, rooted not in soil but in stillness, nourished not by sunlight but by stone, water, and time. High above the sponge forests that rise from the deep seafloor, and far above the drifting realms where jellyfish move like quiet lanterns, another hidden world lives within the ice itself. To the human eye, sea ice appears solid. Its surface stretches in wide white plains, crisp and shining beneath polar winds. Yet inside this frozen expanse lies an intricate network of tiny passageways, microchannels that weave through the ice like threads in a tightly woven cloth. These channels form one of the smallest and most surprising ecosystems on Earth. Within these narrow spaces, creatures live that cannot be seen without magnification. Algae, bacteria, and tiny predators fill the ice with slow-moving life, turning the frozen world into a delicate habitat. Each pore is only a fraction of a millimeter wide, just large enough for a thin film of brine to flow through. This brine is far saltier than the ocean water below, because as ice forms, it pushes salt out into concentrated pockets. The result is a maze of miniature rooms and corridors, where temperatures drop far below the freezing point of ordinary seawater. The organisms that survive here must tolerate both freezing cold and extreme salinity. Many have adapted remarkable strategies to remain flexible and alive in such a harsh environment. Their cells contain special molecules that prevent ice crystals from forming inside them. Their membranes remain soft and fluid even when temperatures fall so low that most life would cease. They move slowly, dividing on rhythms shaped more by the seasons than by their own needs. Algae are among the first inhabitants to flourish within these ice pores. They drift into the channels when the ice begins to form, carried upward by currents as winter deepens. Once inside, they settle onto the walls of the pores, forming thin green or golden layers. Even in such dim conditions, they can capture faint traces of light filtering down from above. They use this light to produce energy, their small bodies glowing gently when viewed under certain conditions. These algae become the foundation of the microchannel food web. Bacteria gather in the same spaces, feeding on organic material released by the algae. Some bacteria break down chemicals within the brine itself, using the concentrated salts or minerals to obtain energy. Others scavenge from dead or dying cells, recycling nutrients back into forms that algae can use again. This cycle continues throughout the winter, slow and steady, as the days darken and temperatures fall. Tiny predators also live within these channels. They are often single-celled or only slightly larger, gliding through the brine with delicate appendages. Some stalk algae, while others feed on bacteria. Their movements are so small that they create ripples the width of dust motes. Yet within the ice, these motions shape the balance of the ecosystem. Every shift in population, every pulse of growth, echoes through the microchannels like a whisper carried between chambers. The seasonal changes of Antarctica test these creatures in ways few other ecosystems experience. During winter, the ice grows thicker, the channels narrow as the brine becomes saltier, temperatures fall lower, pressing the inhabitants into a state of near stillness. Many organisms enter a protective phase. Algae slow their photosynthesis, bacteria reduce their activity to a minimal level. Predators become sluggish, drifting rather than hunting. The microchannel system becomes a world of suspended motion. As spring approaches, the sun returns. Light trickles through the snow and ice, reaching the algae once more. They awaken slowly, beginning to photosynthesize again. The warmth of the season causes the ice pores to widen slightly, diluting the brine. Bacteria resume their steady work, breaking down organic matter accumulated during winter. Predators glide with renewed energy. The changes ripple through the entire system, and soon the channels are filled with quiet activity. Eventually, as summer deepens, the sea ice begins to melt. The microchannels grow larger and start to drain. Many of the organisms that once lived inside the ice are released into the surrounding sea. Algae drift downward, becoming food for grazing zooplankton. Bacteria disperse into the water column. Tiny predators join the currents, continuing the food web far beyond the frozen walls that once held them. Their release into the water provides a pulse of nutrients that helps jumpstart the open ocean ecosystem each year. The organisms that lived in the ice for months shift into new roles, supporting larger animals and linking winter's hidden world to summer's abundance. The resilience of these creatures is remarkable. They survive temperatures lower than most life can tolerate. They endure salinity levels that would dehydrate ordinary cells. They wait through long seasons of darkness, relying on slow metabolism and protective molecules. Then, with the return of light, they awaken and rebuild, filling the ice pores with life once again. Within these microscopic chambers, a miniature world thrives, shaped by patience and adaptation. It is a reminder that even in places where life seems impossible, delicate ecosystems persist. The sea ice becomes not merely a barrier between air and ocean, but a home, a cradle for some of the smallest and toughest organisms on the planet. In the quiet spaces of the frozen Antarctic, life unfolds in sizes too small to see, yet large enough to sustain entire seasons of the sea. Deep beneath the frozen ceiling of Antarctica, far below the narrow pores where tiny algae survive, and far beyond the forests of ancient sponges, lies a realm even more improbable. It is a place without light, carved into the underside of the continent by slow-moving rivers of ice. These hidden corridors stretch for great distances, connecting subglacial lakes and deep seawater in a quiet network of passages that have never seen the sky. For a long time, scientists believed these passages were too cold, too dark, and too nutrient-poor to support anything larger than microbes. Then a probe descended into the Willen's ice stream. At first, the camera showed only swirling grains of sediment, stirred by the water flowing gently beneath 600 meters of ice. The light from the probe illuminated a narrow tunnel, its walls smooth and pale, carved by pressure and the movement of meltwater over many centuries. Everything seemed silent, a world shaped entirely by cold and time. Then something moved across the frame. It was small, perhaps the length of a fingernail. At first, it appeared as a pale shape drifting past the camera. But when it flicked its tiny limbs and darted forward again, the research team watching the footage went quiet. The creature looked like an amphipod or a shrimp, swimming freely through water that should have been nearly empty. A few moments later, another appeared, then another. They were clearly alive, not debris or loose sediment, but active swimmers navigating the pitch-black passage beneath the Willen's ice stream. Their bodies reflected the probe's light in soft flashes as they turned. They approached curiously, then darted away again, disappearing into the shadows. The discovery felt like watching a secret unfold in real time. The presence of these shrimp-like creatures challenged almost every assumption scientists had about such environments. For years, the model had been simple. Without sunlight, these waters could not support large food webs. Without steady nutrient flow, only bacteria or chemical feeders could survive. Without open access to the sea, nothing with complex movement or specialized feeding structures should endure. Yet here they were, swimming calmly in a passage sealed off from the sky by hundreds of meters of ice. Their existence raised quiet questions. How did they find enough food? How did they arrive in these hidden rivers? How did they survive the crushing darkness and cold that defined their world? Some clues came from studying the water surrounding them. The passage beneath the Willen's ice stream was not a stagnant chamber but a moving corridor. Meltwater from the ice sheet carried minerals and organic traces from distant regions. Subglacial lakes upstream released pulses of sediment-rich water carrying nutrients that microbes could process. As bacteria grew and decayed, they formed the first layer of a hidden food chain. Tiny drifting cells, fragments of organic matter, and chemical byproducts created enough nourishment for small grazers. The shrimp-like creatures may have fed on these microbes, scraping them from sediment or filtering them from the water. Their survival suggested that even in a world without sunlight, nutrient cycles could stretch farther and support more diverse forms of life than once believed. Their presence also revealed something profound about Antarctic connectivity. For a long time, the under-ice world was thought to be partitioned into isolated pockets. Each lake, each river, each chamber existed on its own, sealed away by cold and pressure. But the movement of these small creatures hinted at connections between distant regions. They might have traveled through networks of meltwater channels, using currents that shift slowly across centuries. They might have carried genetic traces from the ocean deeper inland, linking ecosystems that scientists once considered separate. If these animals reach the Willen's ice stream from the sea, it means the flow of water from under the ice shelves into subglacial rivers is more dynamic than previously understood. If they evolved within these hidden passages, their adaptation would represent one of the most extreme examples of resilience ever found in cold environments. In either case, their quiet swimming revealed bridges across Antarctica's deep interior. The footage also encouraged researchers to reconsider how life arranges itself in extreme environments. Perhaps shrimp-like creatures do not require constant sunlight or abundant nutrients or wide-open seas. Perhaps they can survive on sparse microbial growth and rely on slow metabolisms shaped by cold. Their steady movement through the water suggested confidence born from long adaptation rather than chance. As the probe continued its journey, more animals came into view, moving through the corridor as though it were not an extreme environment at all but their natural home. They drifted through beams of light, then vanished into the dark again, leaving behind only the faint shimmer of disturbed particles. Their appearance marked a turning point, What scientists once imagined as isolated, barren spaces beneath Antarctica were revealed as connected habitats. Meltwater rivers, lakes, and deep seawater interacted in ways still only partly understood. The shrimp like creatures were living proof that the under ice world was not empty but threaded with life, carried by currents that flowed silently beneath the continent. In the vast stillness under 600 meters of ice, these small animals swam with gentle purpose, offering a glimpse of life's ability to take root in even the quietest and coldest places. Beneath the heavy ice and within the slow moving currents of Antarctica, certain creatures grow to sizes that seem out of place in such a quiet, nutrient limited world. A sea spider as wide as a dinner plate, an amphipod the size of a human hand, jellyfish with bodies that drift like pale lanterns in the dark. These animals do not follow the familiar rules of warmer oceans. Instead, they belong to a phenomenon known as polar gigantism, a pattern in which invertebrates that are small elsewhere reach remarkable sizes in the cold southern waters. To understand this world of giants, it helps to imagine the environment in which they were shaped. The Antarctic Sea is intensely cold, with temperatures hovering just below the freezing point of seawater. Cold water can hold more dissolved oxygen than warmer water, and this abundance of oxygen seeped into the bodies of animals over countless generations. For creatures that rely on diffusion to breathe, such as sea spiders and many crustaceans, oxygen becomes a gentle engine that supports growth. In warmer regions, oxygen limits the size of these creatures. As they grow, their bodies struggle to move enough oxygen inward to support their tissues. The limits of diffusion put a cap on their dimensions. But in the icy Antarctic waters, oxygen diffuses more easily. Larger surface areas allow these invertebrates to absorb enough oxygen to support bigger bodies. Instead of struggling to grow, they expand slowly, their forms lengthening and widening as they adapt to the cold. The cold also slows metabolism. Most animals need warmth to move quickly, digest food, and grow. In Antarctica, growth becomes a long, patient process that stretches across many years. The creatures grow slowly, but they continue growing throughout their lives. They do not burn energy in sudden bursts. They conserve it, building their bodies layer by layer in the stillness of deep water. This metabolic slowdown serves several roles. It lowers the energy needed for survival, allowing the animal to thrive on limited resources. It reduces internal stress, giving tissues more time to develop. It lets large structures form without the risk of overheating or exhausting the animal. In temperate ecosystems, large invertebrates often face metabolic constraints. Their bodies demand more oxygen and food than the environment can provide. But here, cold water solves both issues at once. Oxygen is abundant, and energy demands are low. This balance between cold temperature and oxygen creates an environment where large invertebrates are not only possible, but practical. A sea spider that might reach only a few centimeters across in warmer seas can grow to impressive width in Antarctic waters. Amphipods, which in most parts of the world remain small and delicate, become sturdy and bold, drifting through the water with long limbs and colorful shells. Even certain worms and soft-bodied creatures show similar patterns of exaggerated size. Comparing these giants to their temperate relatives reveals stark differences. In warmer oceans, life moves quickly, metabolisms race with the heat, prey must flee swiftly to survive. Predators must pursue with equal speed. In such environments, small size allows agility and rapid reproduction. Growth is often focused on efficiency rather than scale. In the Antarctic, however, slowness becomes a safety. The calm pace of the food web, shaped by low temperatures and limited nutrients, removes the pressure for speed. Size becomes an advantage in holding on to resources, surviving long periods without food, and navigating cold waters. However, the true causes of polar gigantism remain a subject of ongoing scientific debate. Some researchers argue that oxygen is the primary factor, pointing to studies that show a clear correlation between oxygen availability and body size in many groups of invertebrates. Others believe that the cold itself plays a more intricate role, influencing everything from growth cycles to predation pressures. There are also theories suggesting that the absence of certain predators in Antarctic waters gave some invertebrates the freedom to grow without constraint. Still others point to evolutionary history. Antarctica has been isolated by the Antarctic circumpolar current for millions of years. This separation created a unique evolutionary laboratory where cold adapted species developed without the competition seen in more temperate regions. Gigantism may be the outcome of ancient lineages responding to an environment that encouraged slow, steady growth. One mystery that continues to inspire discussion involves exceptions to the rule. Not all Antarctic invertebrates exhibit gigantism. Some remain small, delicate, and unchanged in size compared to their warmer relatives. Why certain species grow large while others do not is still unclear. It may be related to feeding strategies, reproductive patterns, or even the microhabitats they occupy within the larger under-ice landscape. Despite these uncertainties, the giants of Antarctica offer a captivating glimpse into how life reshapes itself under extreme conditions. They move through the shadowed waters with slow, deliberate grace, their bodies built on principles that differ from the rest of the world. They are reminders that cold does not only limit, but also transforms. It stretches time, alters energy, and allows forms to rise that could not exist elsewhere. In this serene and ancient environment, polar gigantism becomes a quiet testament to life's ability to evolve along unexpected paths, guided by cold currents and deep time. Beneath the frozen surface of Antarctica, where the ice stretches in calm white plains and the ocean below moves with slow, steady breaths, there lies another hidden network. It is older than the great sponge forests, deeper than the drifting realms where shrimp-like creatures glide, and quieter than the dark passages filmed by distant probes. This network is made of rivers, long channels of meltwater that flow beneath the continent itself. They are silent, invisible from above, yet they shape the life and landscape of the under-ice world in ways both gentle and profound. These rivers do not flow like rivers on the surface. There are no rushing bends or glittering reflections, no sunlight dancing along their currents. Instead, they move beneath several kilometers of ice, guided by small changes in pressure and the subtle warmth rising from the earth below. Some rivers are narrow, sliding quietly along smooth beds of ancient rock. Others widen into long under-ice valleys, slow-moving and filled with dark water that has not touched the open air for thousands of years. As the rivers move, they connect subglacial lakes, draining one into another before eventually carrying meltwater into the sea. Scientists first discovered hints of these channels by observing how the ice surface shifted over time. Small rises and falls revealed movement below, like a breath passing through a chest of frozen stone. Later, radar instruments revealed the intricate lines of these waterways, some stretching for hundreds of kilometers. They form a quiet circulatory system beneath the ice, one that moves at a pace shaped by cold and steady pressure. Inside these rivers, the darkness is absolute. No beam of sunlight can reach them. Even the faint glow produced by bioluminescent organisms in shallower waters rarely appears here, yet the rivers are not still. Turbulence, soft and muffled, moves through them. Water flows from lakes with slightly higher pressure into low-lying basins, carving smooth paths through sediment and stone. Tiny particles drift in the currents, lifted and lowered with gentle swirls. Over many years, these movements shape the riverbeds into winding forms, creating channels that may persist for millennia. Despite the harshness of these conditions, some creatures use these rivers as hidden routes. When scientists lowered instruments into certain subglacial systems, they found traces of life carried within the water. Cells from microbial mats, drifting algae fragments, and even signs of crustaceans have been detected far inland, where no one expected them to survive. The shrimp, like animals seen beneath the Willen's ice stream, may have reached that passage through a long chain of channels, carried partway by currents and traveling the rest through slow, patient movement. These migrations are not like migrations in the open sea. They happen across immense stretches of time. A creature might drift through one channel during a season, then settle in a basin for years before moving again. If the water beneath an ice shelf shifts or a lake drains into another, the pathways change, opening new connections and closing old ones. The animals that inhabit this world adapt to these shifting networks, using the quiet flow to reach new pockets of food or shelter. In this way, the rivers offer a kind of invisible bridge. They connect areas that appear isolated, creating unexpected continuity across the under-ice landscape. Microbes from a deep lake may eventually reach the ocean. Marine organisms may find their way inland. Even chemical signatures, such as minerals dissolved in the water, travel along these paths, nourishing microbial communities far from their original sources. Life beneath the ice is not scattered into isolated pockets, as once believed, but linked by a web of movement that unfolds slowly over time. The rivers also carry clues about Antarctica's ancient past. Along their paths, researchers have found patterns in sediment that suggest these waterways once flowed more freely, perhaps at times when the ice sheet was thinner or shaped differently. Some narrow channels appear to have carved their roots long before the modern ice formed, hinting at drainage systems that existed when Antarctica was warmer and less isolated. These ancient paths now lie beneath layers of newer ice, preserved in silence, yet still influencing how water moves today. Other channels appear younger, formed as the ice thickened and pressed downward onto the continent. These rivers cut through sediments left behind by glaciers, reshaping the land beneath them over thousands of years. Their roots offer a record of how the ice has shifted, expanded, and retreated across deep time. By studying the patterns carved into the bedrock, scientists can trace the history of meltwater flow back to ages when the Antarctic climate was vastly different from today. In some places, the rivers drain directly into the sea beneath ice shelves. Here, meltwater mixes with cold ocean currents, creating small zones of turbulence that can stir nutrients upward. These areas sometimes hold more life than surrounding regions, becoming quiet gathering points for creatures searching for rare bursts of sustenance. The rivers become not just pathways, but sources of renewal. Still, for all their movement and influence, the rivers remain deeply quiet. No sound echoes through them except the soft brush of water against stone. No light shines except the occasional glow of disturbed particles. They continue their work without fanfare, carving and connecting, feeding and transporting, shaping a world that remains hidden from the surface. In their silence, they hold the memory of ancient climates, the resilience of hidden creatures, and the subtle flows that knit Antarctica's under ice realm into one continuous, patient system. Far beneath the still rivers of meltwater and the drifting organisms that wander through Antarctic darkness, there exists a realm shaped by forces far older and more powerful than ice. It lies in pockets of the deep sea, where the ocean floor breaks open in thin lines and gentle fractures. Through these cracks rises heat, soft but persistent, escaping from the warm interior of the planet. In a world defined by cold, these places become rare oases, glowing not with light but with energy carried upward through vents in the seafloor. These are hydrothermal vents beneath Antarctic waters. They do not roar with flame or burst with molten rock. Instead, they release warm, mineral rich fluid into the deep ocean, creating shimmering plumes that drift into the darkness. The water emerging from these vents carries strange chemicals that would be toxic to most life near the surface. Yet here, in the silent deep beneath the ice, these substances become food, warmth, and shelter. Picture a vent rising from the ocean floor like a dark chimney surrounded by billowing clouds that shift between pale silver and soft blue beneath the faint light of remote cameras. Around it, the water grows slightly warmer, just enough to create narrow bands of comfort. In these bands, life gathers in forms that seem older than the ice above, as if drawn directly from Earth's early past. Tube worms are among the most striking inhabitants of these oases. They rise from the seabed in tall, slender structures that look almost like delicate towers. Their bodies are hidden inside long, white tubes that anchor them to rock. At the top, a plume of soft tissue extends outward, catching minerals and chemicals carried in the vent's warm water. These plumes sway gently, moving with the deep currents, glowing faintly when illuminated by a passing submersible. The tube worms themselves have no mouths or stomachs. They do not feed in the way most animals do. Instead, their survival depends on symbiotic partners living inside their tissues. These chemosynthetic microbes process the strange chemicals rising from the vents. They use the energy stored within hydrogen sulfide, methane, and other minerals to build sugars and nutrients. The worms rely entirely on these internal companions to convert the raw chemistry of the earth into life. In return, the tube worms offer them a safe home, steady warmth, and a constant flow of vent water. Through this partnership, the vent community becomes an ecosystem powered not by sunlight, but by the planet's inner heat. Around the tube worms, other creatures gather. Certain crustaceans scuttle across the rocks, feeding on microbial films that coat the vent structures. Thin-bodied fish weave between the chimneys, navigating the sharp contrast between warm vent water and the freezing sea around it. Some organisms cling to rocks dusted with minerals that crystallize as vent water meets the cold. Others drift in and out of the plume, taking advantage of brief pockets of warmth. The chemicals released by these vents are central to the survival of every species living nearby. Hydrogen sulfide, which would harm most surface life, becomes the foundation of the food web. Iron and manganese settle around the vents in thin metallic layers. Methane bubbles upward in quiet streams, feeding yet more microbial communities. The sea here is like a vast laboratory, shaping organisms that can thrive in conditions that appear hostile at first glance. In this strange warmth, life behaves differently. Growth patterns shift, behaviors evolve. Some creatures cluster near the vents, gathering close to the source of energy. Others hover farther out, balancing the need for warmth with the need for oxygen-rich water. Everything moves in a slow dance around the rising plumes. These oases reveal an Antarctic world shaped not only by ice but by fire, a reminder that beneath the frozen surface, the Earth remains alive. Without these vents, this region of the sea would be nearly barren. The temperature is too cold, the darkness too complete, the nutrients too scarce. But with the vents, entire communities endure in a place that would otherwise fall silent. Their existence also suggests that Antarctica's deep past was more dynamic than we often imagine. Long before the continent became encased in ice, volcanic activity shaped its landscape. Rivers of lava cooled into dark basalt, mountains rose and eroded, and beneath it all, the Earth's heat continued to move upward, creating opportunities for life in places untouched by sunlight. Even now, these vents hint at the possibility that life elsewhere in the universe might not need starlight. If organisms here can survive on chemistry alone, then icy moons with subsurface oceans may hold similar oases, warmed by tidal forces and fed by hydrothermal activity. In the quiet Antarctic deep, the volcanic oases glow with ancient warmth. They offer refuge, energy, and mystery. They remind us that life can find footholds in the most unlikely places, warming itself against the Earth's inner breath while everything around remains cold and still. Beneath the frozen ceiling of Antarctica, past the volcanic oases warmed by the Earth's breath, there stretches a realm where life takes its time. Here, in the stillness of deep water and the quiet of subglacial worlds, creatures follow rhythms unlike anything on the surface. Their bodies move slowly, their hearts beat at long intervals. Their lives unfold across decades, sometimes even centuries, shaped not by urgency but by patience. These are the slowest lives on Earth, sustained by a metabolism so gentle that time itself seems to stretch around them. Cold is the first sculptor of this stillness. In the deep Antarctic oceans, temperatures hover just above freezing. For most organisms elsewhere, such cold would slow basic processes to a crawl or halt them entirely. But in this environment, slowing down became an advantage. Every movement costs less energy when it happens slowly. Each heartbeat lasts longer. Each breath becomes a careful exchange shaped by the need to conserve rather than to rush. Some fish beneath the ice may take many years to reach maturity. Their growth lines, etched faintly into their bones, reveal a life lived at a pace few other creatures experience. A toothfish, drifting beneath the shelves, may live longer than many land mammals. Similarly, certain sponges grow so slowly that their lifespans stretch beyond the rise and fall of human civilizations. Each new layer of tissue becomes a quiet timestamp, marking the long passage of Antarctic winters. This gentleness is not a weakness but a strategy. Food is scarce in these waters. Organic particles arrive slowly, drifting down from distant parts of the ocean. Microbial mats rebuild nutrients grain by grain. Chemical energy rises only where vents push warmth into the cold. In such a landscape, creatures cannot afford to waste energy. They thrive by making each calorie last as long as possible. Their metabolisms shift into low gear, allowing them to survive long periods without feeding. Even when food becomes available, digestion may unfold gradually, with nutrients absorbed at a rate suited to the chill. The biology of stillness shows itself in many forms. Amphipods, sometimes the size of a human hand, move through the water with deliberate strokes. They do not dart or flee with sudden bursts of energy. Their limbs sweep gently, guiding them through the dark like drifting leaves in a slow current. Sea spiders tiptoe across the seafloor, their long legs carrying them in careful arcs. Their movements conserve energy while providing just enough motion to search for food or avoid a disturbance. Even the microbes living within this world follow these same softened rhythms. Some divide only once every long stretch of time. In warmer oceans, microbes might reproduce rapidly, filling available space with new generations. Beneath the Antarctic ice, each division becomes a significant event. A single microbial colony might take centuries to form a mat visible to the naked eye, growing slowly as minerals and organic fragments become available. What binds all these organisms together is the way cold rewrites the rules of life. In warmer regions, animals must move quickly to avoid predators or to chase prey. Heat accelerates chemical reactions, driving metabolism at a rapid pace. Growth occurs faster, lifespans shorten, reproduction happens frequently. But in Antarctica, none of these pressures exist in the same form. Predators move slowly, prey moves slowly, chemical reactions unfold gently, growth happens over long periods, life stretches itself out. This slow existence shapes behavior as well as biology. A creature that spends decades growing does not need to rush when searching for food. A sponge anchored to the seafloor does not need to compete aggressively for space because the surrounding cold keeps growth rates low for everyone. The pace of life is shared across species, creating an ecosystem where patience becomes the dominant principle. Some animals even enter periods of near suspended animation. During long stretches of scarcity, metabolism slows further, heart rates drop, movements become infrequent. These creatures rely on stored energy and careful regulation to endure. When conditions improve, they return to their slow routines without harm. This ability to pause, to almost step out of time, is one of the great secrets of Antarctic resilience. The slowest lives on Earth also offer insights into longevity. Many Antarctic creatures live far longer than their relatives in warmer waters. The reduced stress on their bodies allows tissues to endure. Cells repair themselves more effectively when not constantly pushed by metabolic heat. Life becomes not a sprint, but a drifting, steady journey. Some deep water corals and sponges in polar regions may be among the oldest living animals on the planet, anchoring themselves in the same places for centuries. These slow lifespans reveal a world where evolution favors endurance over haste. Instead of racing to reproduce before danger arrives, Antarctic creatures invest in longevity, stability, and resilience. Cold grants them the space to grow at their own pace. In this frozen world, where sunlight barely touches the edges of the ice and chemical energy emerges only in scattered pockets, life thrives not by breaking the harsh rules of the environment, but by bending to them gently. The cold does not simply limit life, it transforms it, shaping organisms that flourish through stillness, patience, and quiet persistence. Here, beneath Antarctica, time unfolds differently, and the creatures that call it home show us that life does not always need speed to endure. Sometimes it survives best by moving slowly enough to hear the rhythm of the ice. Far beneath the cold present of Antarctica, beneath its slow rivers of meltwater and the creatures that live at the edge of stillness, rests a memory the continent has carried for millions of years. It lies locked in rock, sealed within sediment, and scattered across ancient shorelines now buried under snow. These memories come in the form of fossils, the remains of creatures so large and unexpected that they reshape how we imagine this frozen land. Long before ice claimed the continent, Antarctica was home to giants, both on land and in the warm seas that once washed gently along its coasts. Among the most striking of these giants were the enormous penguins. Their bones reveal bodies far taller than any living species. Some stood as high as a person's chest, their heavy frames built for diving through warm coastal waters. Their wings, shaped like sturdy flippers, powered them deep below the surface. Their feathers trapped warmth in a world that had no ice. When they swam, they resembled dark shapes moving with steady rhythm through sunlit seas. These ancient penguins hunted fish and squid among reefs and kelp forests that no longer exist, leaving behind clues about a time when Antarctica mirrored climates far more temperate than today. Not far from the fossils of these penguins lie the remains of early whales. These whales were explorers of the southern oceans during a period when the Earth was warmer and the Antarctic coastline supported lush ecosystems. Their bodies were smaller than the immense whales of the modern age, yet they carried the unmistakable features of transition. Some fossils show animals that still bore vestiges of hind limbs, reminders of the land-dwelling ancestors from which whales emerged. Others belong to species already fully committed to life in the water, gliding through ancient seas that were rich in nutrients and alive with prey. These warm Antarctic seas seem to belong to a different planet. During certain periods of Earth's history, ocean currents brought warm water to the continent. Forests grew along the coasts. Temperatures were mild enough for reptiles, birds, and early mammals to live among the greenery. Light filtered through broad leaves. Rivers carried gentle flows into calm bays. Life flourished in forms that seem impossible to imagine against today's icy backdrop. As global climates shifted, so did Antarctica. The slow movement of continental plates carried it southward. Atmospheric conditions changed through cycles lasting millions of years. Currents redirected their flow. At some point, the warmth that once surrounded the continent receded. Ice began to accumulate. Seas cooled. Food chains transformed as cold water animals replaced warm water species. The ancient giants either adapted or disappeared, leaving behind fossils that tell the story of their final days in a changing world. Shifting temperatures shaped body size in remarkable ways. In warmer periods, large bodies helped animals maintain a steady internal temperature, avoiding sudden swings caused by sun or shade. Water teemed with life, allowing predators like giant penguins to grow large and strong. Whales fed on abundant prey, building the muscle and bone needed to travel great distances. Even smaller creatures benefited from the warmth, moving through ecosystems dense with plants and plankton. Yet, as the climate cooled, the rules changed. Cold water carries more oxygen, which later allowed invertebrates to grow larger. But for warm, adapted animals, cooling seas brought challenges. Food sources shifted, coastal forests declined. Eventually, the entire environment transformed into the frozen world we know today. The ancient giants left only traces, preserved in stone. Their fossils offer glimpses into worlds that disappeared beneath the ice. A penguin bone lifted from sediment becomes a doorway to a time when the continent echoed with the calls of birds walking along sandy shores. A whale vertebra found near old rock outcrops becomes a hint of ancient migrations through warm currents that no longer flow. Each fossil is a quiet storyteller, carrying within it the memory of climates that rose and fell like slow tides. Beneath today's ice, clues remain about these long-vanished ecosystems. Sediment cores, drawn from beneath thick shelves, contain grains of pollen from forests that grew millions of years ago. Chemical signals reveal water temperatures far warmer than those we see now. Even the shapes of valleys hidden under the ice hint at rivers that once flowed freely across the land. When scientists compare these deep time records with the fossils found along the coast, a picture forms of an Antarctica rich with life and color, long before cold claimed it. This ancient history shapes how we see the frozen world today. The continent is not a static wasteland, but a place of transformation. Beneath its modern stillness lies the memory of forests, waves, and creatures that grew fierce and immense in warmth. The ice may seem eternal, yet it covers layers of stories written in bone and stone. The giants of Antarctica remind us that the world changes, sometimes gently, sometimes dramatically, carrying life along paths shaped by temperature, time, and the quiet turning of the earth. Here, beneath the silence, the past waits, held in the patient hands of ice and rock, offering its tale to those who listen. Beneath the long shadow of Antarctica's ice shelves, where sunlight never arrives and seasons pass without color or warmth, life depends on a delicate cycle that moves so slowly it is almost invisible. It is a cycle built from fragments, whispers, and patient transformations. Here, carbon becomes the quiet currency of survival, carried from one organism to another in a world that receives almost no new material from above. Everything must be reused, everything must be reshaped. Nothing can be wasted. Far from the open ocean, the under ice world receives only small traces of organic matter drifting in from distant waters. These fragments fall like gentle snow through the dark, a broken scale from a fish, a strand of algae swept under by a stray current, the softened remains of a jelly creature that lived its entire life without ever seeing light. Each piece drifts downward until it settles on the seafloor or becomes caught in the folds of microbial mats that coat hidden surfaces. In this lonely place, such fragments are precious. They become the starting point for a slow and patient carbon cycle that has allowed ecosystems to persist for millions of years. Much of the work begins with microbes. These tiny organisms, living in thin sheets on rocks or suspended in still water, take hold of carbon that arrives from above. They break it down grain by grain, releasing nutrients that other microbes can use. In warmer oceans, decomposition might happen quickly. Here, the cold stretches each chemical reaction into slow, measured steps. A single piece of organic material may take years to transform fully, yet the pace does not hinder survival. Instead, it creates a steady flow of nutrients that aligns with the rhythm of every creature that depends on it. Detritus, the soft blanket of broken life on the seafloor, plays a central role in this cycle. It gathers in quiet basins and along the edges of subglacial shelves. Amphipods sift through it, searching for tiny traces of nourishment. Worms and small invertebrates burrow into it, feeding on the microbial colonies that cling to its surface. As these creatures digest what they find, they produce waste that becomes food for yet another layer of microbes. The cycle repeats, gentle and continuous, allowing nutrients to remain in motion even when no new material arrives for long stretches of time. Microbial decomposition forms the foundation of this entire process. In the absence of sunlight, organisms rely on chemical reactions to transform carbon into usable forms. Some microbes use minerals leached from rocks. Others draw energy from oxygen in the cold water. Many work together, passing molecules between species in long, quiet chains that resemble an underground marketplace. Each step releases just enough energy to sustain life, and each step preserves material that might otherwise be lost. This careful recycling allows the ecosystem to remain balanced despite its isolation. Balancing an ecosystem with almost no external input requires remarkable cooperation. Creatures move slowly, conserving energy so that the available carbon lasts longer. Predators hunt only when necessary. Scavengers gather what has already been released by others. Microbes build communities that share resources and survive in thin layers where oxygen is scarce. Even chemical gradients, formed between cold water and warmer pockets near the seafloor, become opportunities for life to extract energy. Everything works in harmony, shaped by the need to stretch limited resources across timescales far longer than those found in most environments. In some areas, carbon becomes isolated beneath the ice shelves for astonishing lengths of time. Thick layers of sediment trap it. Glacial movement buries it deeper. Water circulation becomes so weak that carbon remains stored for centuries. Scientists studying these regions find carbon signatures that are older than human civilizations, preserved in forms that allow glimpses into ancient ocean conditions. When small disturbances finally release this stored carbon back into circulation, it arrives like a slow echo from the past, feeding microbial communities that have learned to use whatever the ocean remembers. This isolation also creates pockets where carbon behaves differently than in open water. Under ice shelves, the weight of the ice and the cold temperatures change how gases dissolve. Carbon dioxide may remain trapped in certain layers, influencing the acidity of microenvironments where only specialized organisms can survive. These pockets support unique microbial populations that depend on conditions found nowhere else on Earth. Their presence adds depth to the under ice carbon cycle, showing how even the smallest variations in temperature or chemistry can shape life in profound ways. Despite the challenges of scarcity, the carbon cycle beneath Antarctica is not fragile. It has persisted through shifts in ice coverage, changes in ocean currents, and the advance and retreat of glaciers. Its strength lies in its balance, built not from abundance but from efficiency. Every molecule is used and reused. Every organism contributes to the quiet recycling that sustains the whole. It is a cycle shaped by patience, guided by the rhythm of the cold, and preserved in darkness. In these hidden waters, carbon is more than a chemical element. It is the thread that links every creature to its environment, weaving connections between past and present. It drifts from hand-sized amphipods to transparent jellies, from slow fish to ancient microbial mats, forming a loop that endures even in silence. Here beneath the ice, where the world moves softly and time stretches like a long breath, the carbon cycle becomes a quiet testament to life's ability to endure, adapt, and find balance in the coldest places on Earth. In the deep Antarctic waters, where light has never touched the seafloor and shadows stretch forever, hunting becomes an art of patience and sensing rather than sight. Here, predators cannot rely on silhouettes or glimmers of movement. Instead, they read the water as if it were a vast and delicate instrument. Every ripple, every shift in pressure, every faint chemical signal becomes a message. In this quiet world beneath the ice, creatures have evolved senses that feel more like intuition than perception, allowing them to find prey without ever seeing it. The darkness shapes everything. Sound travels far in the cold, dense water. Vibrations linger longer than in warmer seas. Chemical traces drift slowly, painting invisible trails behind every living thing. Predators that wish to survive learn to listen with their bodies, their skin, and their nerves. Sight fades in importance until it is no longer a tool at all. What replaces it is a sensory landscape rich in clues that only those adapted to the cold can understand. Many fish here possess a lateral line system that runs along their bodies like a delicate thread. This line is filled with tiny organs that sense the slightest movement of water. A fleeing amphipod creates a ripple. A shifting sponge colony releases a faint disturbance. Even the gentle current created by a jelly drifting nearby leaves a pattern that can be felt by creatures tuned to these signals. In temperate seas, this sense complements vision. In Antarctica, It becomes the primary compass in a world where visibility reaches almost nothing. Chemical cues act as another map. When a creature is stressed, injured, or feeding, it releases faint molecular markers into the water. Some predators have evolved the ability to detect these signals in extremely low concentrations. Their world becomes layered with invisible trails that reveal who has passed through, how recently, and perhaps even what condition they were in. The dark water becomes a record of presence, written not in light but in gentle whispers of chemistry. Pressure also plays a role in this sensory symphony. In deep Antarctic environments, pressure is immense and stable. Any motion that disturbs it, no matter how small, can be detected by creatures adapted to notice such shifts. A toothfish turning its body may create a wave of pressure that travels outward. A squid stirring the water creates a subtle push. Predators that can interpret these patterns learn to distinguish between the signature of prey and the signature of something too large or too fast to pursue. These abilities shape a unique style of hunting. There is no sudden chase, no burst of speed across open water. Instead, predators move with extreme care. They swim slowly, pausing often, letting their sensors gather information before continuing forward. Each movement is deliberate. A predator glides, waits, then glides again, almost as if it is trying not to disturb the water that carries its clues. Some fish have elongated snouts filled with sensory pores that help them locate prey hidden beneath layers of sediment. Others carry long barbels that drift gently through the water, detecting faint vibrations from creatures that burrow or cling to rock surfaces. Even invertebrates display remarkable precision. Antarctic sea spiders extend their long legs across the seafloor, feeling for small, soft-bodied prey that move too quietly to be sensed otherwise. Predation in this world reflects scarcity. Food arrives slowly, populations grow at gentle rates, and every organism has learned to conserve energy. Because of this, predators cannot afford to attack without confidence. They must be sure their strike will count. Many stalk from behind, approaching so carefully that the prey does not sense the change in the water. Others wait motionless for long periods, allowing prey to come close before making a single quiet motion to capture it. There is no wasted energy, no unnecessary pursuit. Every action fits within the rhythm of the cold. Even larger predators behave this way. The colossal squid, though powerful, hunts slowly in its deepest habitats, using enormous eyes to detect faint bioluminescent glimmers and then relying on water disturbances to approach unseen. The toothfish uses careful sweeps of its tail to trace the presence of smaller fish in the gloom. Amphipods, though often prey themselves, become predators when opportunity arises, using touch and vibration to find immobile food resting on the seafloor. In this environment, the silence of the hunt becomes part of the landscape. Predators do not announce themselves with noise or motion. Each has adapted to move as quietly as the drifting ice above. Their survival depends on the ability to blend with the stillness. The ice ceilings, thick with pressure, amplify any tremor, so the creatures below learn to live lightly, blending with the gentlest currents. Scarcity shapes not only behavior, but also relationships between species. Predators may go long periods without feeding, relying on slow metabolism to conserve energy. When they do feed, their movements are precise, shaped by the need to make each opportunity count. Prey animals, in turn, evolve ways to mask their pressure signals or blend their chemical signatures with the water. The arms race between predator and prey unfolds not in bursts of speed, but in careful adaptations that refine the senses. In the permanent night beneath Antarctica's ice shelves, hunting becomes a form of listening. Creatures carve out their place in the world through touch and vibration, becoming part of the quiet patterns that ripple through the dark. Here, survival is written in the water itself, carried in every shift, every swirl, every silent movement that speaks in ways light never could. Far beneath the ice, in places where the seafloor slopes gently into silence, there are moments when the deep Antarctic world seems to move with unexpected grace. These moments are not shaped by animals or shifting tides. They come from the meeting of water and cold, from meltwater slipping downward through the darkness, from the quiet creation of what scientists sometimes call frozen waterfalls. They are not frozen in the solid sense. Instead, they are streams of water so cold and dense that they descend like invisible rivers, falling through the ocean with a slow and deliberate motion, carving pathways no eye can see. These flows begin far above, where pressure and friction melt the base of the ice sheet. Thin films of water gather beneath glaciers, warmed slightly by the weight of the ice itself. Over time, these small streams merge into larger channels. They travel downward until they find openings along the edge of the continent. When this meltwater meets the deep ocean beneath the shelves, the contrast becomes striking. The meltwater is fresh, cold, and often enriched with minerals from the rock it has touched. The ocean water is salt-heavy, just as cold, and dense in a different way. The boundary between the two behaves like a soft veil, creating a division shaped entirely by temperature and salinity. This is where the waterfall begins. The fresher meltwater, although extremely cold, is lighter than the dense salty ocean water surrounding it. But as the two mix, the meltwater cools further and reaches a point where it becomes heavier. It sinks gently, flowing downward in slow currents that can stretch for many kilometers. These invisible rivers do not roar or churn. They fall with a quiet persistence, like threads of cold weaving their way into deeper layers of the sea. Along these boundaries, the rules of the ocean shift slightly. Temperature changes across only a few centimeters. Salt levels shift in delicate gradients. These thin layers guide the movement of drifting life, creating pathways that some creatures follow without ever seeing them. Tiny plankton, carried by the currents, drift along the edges of these descending waters. Microbes gather where fresh meltwater and saltwater meet, finding chemical gradients that provide energy or nutrients. Even larger animals feel these changes. A fish swimming nearby might sense the cool flow against its side and turn instinctively, moving along the boundary as if following an unseen road. The frozen waterfalls become conduits for life, shaping gentle migrations across great expanses beneath the ice. Although no creature can see the flow, they feel it. Slow currents guide them from one isolated pocket of the ocean to another. In a world where connections seem sparse and geography appears fragmented, these currents reveal that the deep Antarctic waters are more linked than they seem. The creatures that drift within these flows often move without intention. A jelly may be lifted slightly upward, then carried downward along the falling water. Amphipods grazing on microbe-rich particles may find themselves traveling along these streams, pushed from one basin to another over many days. Even microbial mats may release small fragments that drift along the gradients, seeding life in distant areas. This movement offers clues about the hidden connectivity of Antarctica's under-ice ecosystem. For many years, scientists believed that each subglacial lake and deep pocket beneath the shelves was completely isolated. The ice above seemed too thick for exchange. The water below seemed too still for travel. Yet the frozen waterfalls show that the ocean moves in ways that are both subtle and profound. Material from one area can eventually reach another. A chemical signature from a distant corner may appear far away, carried quietly by descending currents. This slow, steady mixing suggests that life beneath the ice is not confined but gently spread through channels shaped by hydrographic patterns. Temperature and salinity boundaries also reveal how different environments can exist side by side. A few meters away from the falling meltwater, the ocean may be richer in nutrients. Below it, conditions shift again, becoming more favorable for certain microbes. These layers create stacked habitats, each shaped by the balance between cold, salt, and pressure. Creatures living here learn to navigate these subtle gradients, finding positions where energy is highest or where predators are least likely to wander. As these frozen waterfalls flow across the deep, they leave behind trails of cooler water and redistributed minerals. Over long periods, these flows carve invisible shapes into the ecosystem. They influence where sediment settles, where microbial colonies form, and where drifting organisms accumulate. Their presence becomes part of the slow heartbeat of the Antarctic depths. In this world where change happens quietly, the frozen waterfalls stand as gentle reminders that even in darkness, movement continues. Currents slide through the water without light, carrying life, memories, and minerals from one part of the deep ocean to another. They help weave Antarctica's hidden ecosystems into a larger whole, connecting distant communities in ways that only careful observation can reveal. Here in the deep, where silence wraps around every drifting form, these invisible rivers show that even the coldest places have stories shaped by motion, balance, and the graceful descent of water through the waiting sea. Deep within Antarctica's frozen layers, far below the windswept surface and the drifting snow, lie traces of worlds that no longer exist. These traces are not fossils of bones or shells. They are far smaller, far quieter, and far more fragile. They are fragments of DNA, tiny strands of biological memory sealed in ice for thousands or even millions of years. Each fragment is a molecular time capsule, holding whispers from a past that would otherwise be lost to silence. These time capsules form slowly. Snow falls, presses downward, and becomes firmer with each passing year. Layers build upon layers. At the base of these layers, where the ice thickens into ancient sheets, bits of life once carried by winds or waters become trapped. A grain of pollen that drifted over a forest long vanished. A cell from a drifting plankton. A fragment of algae frozen as seas cooled. Even a microbe washed from a warm, forgotten shoreline may become sealed within the growing ice. The cold preserves what would normally decay, stopping time in a way that feels almost gentle. When scientists drill into these layers and recover ice cores, they pull up stories written in ice instead of ink. Each meter of core rises from the dark like a slender column of preserved history. Tiny bubbles record ancient atmospheres. Dust reveals long distant winds. And within the pockets where meltwater once refroze, DNA waits for its chance to speak. These DNA fragments are not whole genomes. They are scattered pieces, sometimes only a few letters long. Yet even a fragment can reveal astonishing detail. When studied carefully, it can show what kind of creature left it, where it lived, and sometimes how it responded to the environment. A single strand may indicate that warm coastal waters once supported algae species, now found only in temperate oceans. Another may trace the presence of microbes adapted to sunlight, telling of a time when the region was not covered in ice, but open sea. In some cores, scientists have found DNA signatures of plants that once grew near the Antarctic coast. These fragments reveal forests that stretched toward the poles during warm periods when the continent was green and alive. Other cores contain genetic traces of animals that traveled near these ancient shores, leaving behind cells that froze into place as climates shifted. These discoveries paint a picture of Antarctica that seems almost dreamlike compared to the world we see today. There are surprises as well. In ice that has remained undisturbed for long stretches of time, researchers sometimes uncover DNA from species that are entirely unfamiliar. These fragments may belong to lineages that vanished before humans existed, or to organisms that still live in hidden pockets beneath the modern ice. Some genetic signatures do not match any known species, suggesting that the deep Antarctic past was filled with creatures whose stories remain incomplete. Each fragment becomes a clue, waiting for the rest of its story to be uncovered. Even more intriguing are the DNA traces found in ice layers close to the deep ocean. Some fragments come from microbes that live in subglacial lakes or under ice seas today. Their presence in older layers hints that these environments have remained active for a long time. Life persisted even as ice thickened and currents shifted. The past and present blur together, weaving a continuity that stretches across millennia. This blending reveals a boundary that is not sharp but delicate. Ancient DNA preserved in old ice sits side by side with fragments from modern organisms drifting in through cracks or meltwater channels. Sometimes the two mingle. The old fragments remain silent, unable to awaken, but still carrying the shapes of their vanished ecosystems. The new fragments tell of a world that continues to change, adapting to the cold and the long night beneath the shelves. Together, they form a quiet dialogue. The ancient fragments speak of warm seas, forests, and open coastlines. The modern fragments speak of frozen lakes, deep currents, and creatures shaped by darkness. The ice itself holds both stories without choosing one over the other. It becomes a library of Earth's shifting moods, preserving memories from times when Antarctica was warm, times when it was cooling, and times when it became the frozen realm we know today. As researchers melt a section of core to study its contents, the ancient water flows again for the first time in ages. Within it swim molecules that once drifted freely in sunlight or swayed with gentle tides. These molecules cross the boundary between ancient and modern life, reminding us that the world above the ice is only the latest chapter in a much longer story. In the stillness beneath Antarctica, time settles into layers. DNA, preserved in cold transparency, becomes a bridge between worlds that no longer meet. Through these fragile threads, the past continues to breathe softly, allowing us to glimpse lives that faded long before the ice arrived. Long before ice tightened its grip around Antarctica, long before continents drifted into their present shapes, Earth was a place of shifting seas and new experiments in life. The planet's earliest oceans were cold, dim, and rich in minerals drawn from restless rock. Sunlight struggled to reach deep water. Simple organisms survived by drawing energy not from the sun, but from chemistry hidden in stone and sediment. When we look beneath Antarctica today, into its dark lakes and under ice seas, we find conditions that echo those ancient ages. The creatures that thrive here have become living reminders of what Earth once felt like, and of how life learned to persist in a world far less friendly than it is now. The extreme environments beneath the Antarctic ice offer a mirror to those early oceans. In subglacial lakes, darkness is complete. Temperatures hover near freezing. Water chemistry is shaped more by contact with rock than by any influence from the surface. Microbes feed on minerals, building energy from reactions that unfold slowly in the cold. These are the same types of strategies used by early life, long before the first plants or complex animals appeared. When we study Antarctic microbes, We are not simply exploring a unique ecosystem, we are looking into a deep reflection of ancient Earth, preserved not in rock but in living communities that continue to function as they did millions or even billions of years ago. The dark waters beneath the ice shelves act as cold analogs to the primordial seas. Early Earth had long stretches where sunlight struggled to penetrate thick layers of atmospheric haze. The oceans then were not bright blue expanses, but dim, greenish basins filled with chemical gradients and slow moving currents. The organisms that survived those conditions relied on simplicity and patience. They grew slowly. They used energy sparingly. They built networks of interaction that allowed small exchanges of nutrients to support entire communities. The ecosystems beneath Antarctica echo this rhythm. Microbial mats grow in thin sheets, adding new layers over centuries. Chemosynthetic organisms extract energy directly from minerals or dissolved gases, transforming barren surroundings into sources of nourishment. Even larger creatures, such as amphipods or icefish, depend on food webs that move gently and steadily, shaped by scarcity and quiet cycles of decomposition and renewal. Studying these creatures helps us understand how life overcame the early challenges of our planet. Their ability to survive without sunlight offers clues to how the earliest organisms endured before photosynthesis became widespread. Their reliance on mineral energy sources suggests how life may have first taken hold around hydrothermal vents or in sheltered pockets where warm rock met cold water. Their slow metabolisms reflect strategies that may have once been universal before Earth warmed and surface life expanded into brighter and more varied environments. There are lessons in adaptation here as well. Antarctic species have evolved to handle extreme pressure, freezing temperatures, and a lack of steady nutrients. Their bodies reveal solutions that differ from those found in temperate or tropical ecosystems. Some produce antifreeze molecules that keep their cells from forming damaging crystals. Others shape their bodies to take advantage of oxygen-rich cold water. Still others grow larger in response to slow metabolism and stable conditions. These adaptations remind us that survival is not about speed or strength alone. It is about finding ways to fit into the environment, however harsh or unusual it may be. The resilience of these ecosystems tells a deeper story. Beneath the ice, life persists through long cycles of isolation. Lakes may remain sealed for millions of years. Under ice seas may be cut off from open water by thick shelves that shift only slowly. In these closed worlds, life continues with remarkable steadiness. Nutrients are recycled endlessly. Energy is shared among microbes, invertebrates, and larger animals in a quiet loop that needs no external support. This endurance shows that life can remain stable even when conditions appear nearly impossible. These resilient communities also help us understand how environments recover after global changes. Antarctica has gone through warm periods, cold periods, and transitions between the two. Each shift reshaped its ecosystems, yet traces of ancient strategies linger. When we analyze DNA preserved in ice or study the chemistry of subglacial water, we see hints of organisms that adapted during times of warmth and survived through long periods of cold. This continuity reveals that life can endure dramatic climate changes by shifting its strategies, slowing its pace, or finding new sources of energy. The creatures beneath the Antarctic ice remind us that life on Earth has always been inventive. They show that survival does not depend on perfect conditions. It depends on flexibility, cooperation, and patience. They reveal how ecosystems can flourish even when resources are scarce and environments are harsh. and they offer a window into the earliest days of our planet when life was still learning how to exist in a world without certainty. In the stillness of Antarctica's deepest waters, the past feels close. Each drifting microbe, each slow moving invertebrate, each fish shaped by cold becomes a quiet storyteller, carrying lessons from ages when Earth was young. These creatures are guardians of ancient knowledge, teaching us how life began, how it adapts, and how it endures. Beneath Antarctica's ice, where darkness stretches endlessly and life survives through quiet ingenuity, we find a world that does not feel entirely earthly. Its still waters, its hidden lakes, its slow-moving communities of creatures, all exist far from sunlight and warmth, yet they thrive. They build food webs from chemical energy, endure pressures that would crush most life, and persist in isolation for spans of time longer than human history. When scientists study these fragile, persistent ecosystems, they are not only learning about Earth, they are learning how to search for life elsewhere, far beyond our planet. Orbiting the giant worlds of Jupiter and Saturn lie two moons that have captured the imagination of explorers. Europa, covered by a shimmering shell of ice, hides a global ocean beneath its surface. Enceladus, smaller and brighter, sends plumes of water vapor into space from cracks near its south pole. Both moons appear to have liquid water locked beneath layers of ice, warmed from below by tidal forces and chemical reactions. When we imagine what those oceans might be like, the closest comparison is not a warm tropical sea on Earth, but the hidden waters of Antarctica. Here, beneath the ice shelves and within subglacial lakes, life thrives in environments that resemble what Europa or Enceladus might offer. There is no direct sunlight. There is only cold, stone, water, and chemistry. Microbes draw energy from minerals. Larger creatures survive because these microscopic communities generate enough nourishment to support them. Entire ecosystems form without ever relying on the sun. This type of survival, known as chemosynthesis, becomes a universal story. It suggests that life does not need light. It needs only a source of energy and the ability to use it slowly and carefully. Chemosynthesis may be the key that connects Earth to distant worlds. On early Earth, before photosynthesis took hold, chemosynthetic microbes likely dominated the oceans. In Antarctica, we see descendants of this ancient strategy still thriving today. They live along mineral-rich sediments, near vents where chemical gradients form, and in lakes where organic material is scarce. Their quiet endurance shows that life can build itself from the simplest resources. If similar conditions exist beneath the icy crusts of Europa or Enceladus, then the potential for life becomes more than speculation. It becomes a continuation of a pattern we see in Earth's harshest places. Antarctica also teaches us about the limits of habitability. Life here survives near freezing temperatures, in perpetual darkness, and with minimal nutrient input. It does not rely on sunlight cycles or surface weather. Instead, it depends on stability, slow metabolism, and careful recycling. These traits may be common on other worlds. Europa's ocean, insulated by a thick ice shell, might remain stable for millions of years. Enceladus may host hydrothermal vents at its seafloor, where water meets warm rock. These environments could mimic the Antarctic deep, where chemical energy rises softly into cold water and becomes the foundation for life. Studying Antarctica's hidden ecosystems helps scientists understand how energy cycles might operate on other worlds. In subglacial lakes, minerals feed microbial communities that grow slowly but persistently. On Europa, similar chemical gradients might exist where water interacts with the rocky mantle. In Antarctica's under-ice seas, creatures rely on nutrients that drift from distant waters or rise from the seafloor. On Enceladus, Plumes of water may carry similar traces of chemistry upward, creating an opportunity for life to spread. Antarctica also offers practical lessons for exploration. Drilling into subglacial lakes requires extreme care to avoid contamination. Instruments must be sterile. Sampling must be done gently. These methods reflect what future missions to icy moons will need. Landers that reach Europa or probes sent through Enceladus's plumes must be designed with the same caution. The experience gained from exploring Antarctica will help guide how we approach alien oceans with respect and scientific precision. There are broader implications for how we imagine life. The creatures beneath Antarctica show that survival does not require warmth or abundance. It can unfold quietly, in slow rhythms shaped by cold and pressure. This expands the idea of habitability beyond our familiar surface environments. An icy world is not a barren world. A dark ocean is not an empty one. Antarctica demonstrates that life can emerge wherever there is water, chemistry, and time. Future missions to Europa and Enceladus may carry instruments that search for the faint signatures of life. They will look for organic molecules, chemical imbalances, and perhaps even fragments of cellular material drifting in the water. If they find anything, it may resemble the life that thrives beneath Antarctica's ice. Simple, resilient, and shaped by the deep. In this way, the creatures of Antarctica become guides. Their quiet existence helps us imagine the possibilities beyond Earth. Their endurance shows that life can persist in worlds that seem inhospitable. Their strategies reveal how survival takes root in darkness. As we continue to explore the coldest corners of our own planet, we prepare ourselves to recognize life in the distant oceans hidden beneath the icy shells of other worlds. Far below Antarctica's frozen surface, where the world lies in perfect stillness, we have wandered through an environment shaped by cold, silence, and astonishing endurance. Each creature we met, each current we traced, each hidden lake and drifting shadow revealed a truth that feels both ancient and comforting. Life, even in its quietest forms, finds a way to continue. It survives without sunlight, without warmth, without the familiar rhythms of the surface. It persists in darkness so complete that time itself seems to move differently. As we traveled gently through these chapters, we glimpsed ecosystems that feel almost impossible, yet they are real and alive at this very moment. We saw fish, whose clear blood flows like cold glass. We watched giant sea spiders glide across the seafloor with measured grace. We drifted beside colossal squid that rule the deep without ever being seen. We witnessed amphipods as large as a human hand, moving in slow spirals through black water, and we discovered the strange, delicate brinicles, forming icy tendrils that shape life and death with quiet certainty. In these places, every movement is subtle. Every cycle unfolds with patience. Every survival strategy reflects the deep relationship between life and environment. Nothing hurries. Nothing wastes energy. Nothing breaks the silence unless it must. Through these journeys, we have also felt the presence of worlds long gone. Fossils beneath the ice revealed Antarctic giants that once roamed warm seas and lush coastlines. Molecular fragments preserved in ancient ice offered soft echoes from distant climates and vanished ecosystems. The past and present coexist here, as though the ice holds both stories gently, allowing neither to fade completely. And yet, even with all we have learned, most of this vast hidden world remains untouched. Humanity has explored only the smallest fraction of what lies beneath the shelves and glaciers. Hundreds of lakes remain unstudied. Entire drainage systems flow unseen through the deep. Underwater mountains and valleys stretch across the dark like maps waiting to be read. There are creatures we have not described, food webs we have not traced, and microbial communities whose strategies may hold answers to questions we have not yet learned to ask. These mysteries remind us how limited our understanding of Earth still is. Our planet is not fully known, it is not exhausted of wonder. Beneath the deepest ice, beneath the widest oceans, beneath layers of time recorded in frozen water, life continues to surprise us. Each discovery expands our sense of what is possible, both here and beyond our world. If you have been listening with us tonight, drifting slowly through these quiet realms, you have shared in something rare. You have seen how life adapts, how it endures, and how it flourishes in conditions that seem impossible from the surface. And now, as this journey comes to rest, I would love to hear from you. Which discovery stayed with you the most? Was it the clear blood of the icefish flowing without color in the cold? The hand-sized amphipods drifting beneath 600 meters of ice? The colossal squid with its immense eyes made for eternal night? Or perhaps the ancient DNA, preserved in time, whispering from long forgotten worlds? Your thoughts, your reflections, and your favorite moments help shape the quiet community we share here. They add warmth to these cold landscapes and bring the stories of distant ecosystems a little closer to home. If you enjoyed exploring these hidden realms with me, you are welcome to return anytime. There are countless mysteries left to wander through, countless stories still resting in the dark. New journeys will come, each one gentle and curious, following the same soft rhythm that carried us through Antarctica's under-ice world tonight. So, if you would like to continue drifting through forgotten oceans, ancient skies, and quiet corners of our planet, feel free to subscribe and stay close. This little sanctuary of science and calm will always have space for you. For now, take one last slow breath, let your shoulders soften, and hold close the thought that even in the coldest places on Earth, life finds a way to glow.